Venkatesh, please mute. Oh yeah.
Hi everyone, my name is Praveen Kumar. Am I audible? Could you guys paste
Yes,
in the
sir.
chat window if I'm audible?
Yeah, sir.
Okay. 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 So instead of pasting or instead of responding directly to me, let's leverage the common chat window that is open for all. I see many responses coming in directly to me, and I'll request everybody to put themselves on mute if when the session is on. If you have any doubt, then please feel free to unmute yourself and ask your doubts. Make the session interactive as much as possible. Okay. So as I was saying, my name is Praveen Kumar. I'm the founder of towardsmachinelearning.org. We have Ankush with us. He'll be presenting you today on object detection algorithms. So there's my introduction in very brief. So before we start, I'll highly appreciate if you guys could give a very little introduction about yourself. So if you're a college student, then you can write the college name and the year and the stream that you are pursuing degree into. If you are a working professional, then write the company name and the number of working experience you have. Can we do that? So it will help us to understand the audience. So we'll start the topic like, if we see there are lots of college students, then we'll start from the scratch and we'll take it to the advanced level depending upon the variation in the participants. Okay, we have the response coming in. Okay. Shivam, could you please put the college name and the year that you are into right now and the stream that you are pursuing your degree into? You can type that into the common chat window instead of replying to me directly. Okay. I see many of you are using direct message. Do not do that. So other people will also get to have an idea, participants are from which college. Shivam, Mohsina, could you guys please, Vijay Lakshmi, could you guys please use the common chat window? Okay. Okay. We have first year students as well. We have people from PhD as well. We have people who are pursuing their MTech final year as well. Okay. I see most of you are college students either in BTech or MTech. Can we have responses from other participants as well? Okay, we have the professors as well from Shri Vidyaniketan Engineering College. Good to see you. Okay. Can we have a response from other participants as well?
Thank you, sir.
Okay. Okay. Then okay, we have mechanical BTech fourth year as well. Okay. So we'll start the topic from scratch maybe. So you guys can understand the topic and we'll take it to the advanced level the way we usually conduct live sessions. I hope many of you are joining us, have been joining us from our first live session itself. So without further ado, I'll hand it over to Ankush, and Ankush, you can start the session maybe.
Yeah, hello. Am I audible?
Hello, sir. Yes, sir.
Yeah, you guys can comment in the chat section. Use that thing. Okay, so I guess I'm audible to all. Welcome you all. Okay, so what do we have today? We are gonna study object detection evolution. The code that brings you here, like brings me here at this point, is ideas don't just happen, they usually evolve. So what do I mean to say is, there wasn't someone who woke up some morning and was like, okay, I have to build this object detection algorithm. So it wasn't like someone came from the scratch and yeah, this is my object detection algorithm. There was too much effort behind it, and we are gonna see that thing. Okay, okay, let's have a simple question. How many of you know about YOLO algorithm or heard about YOLO algorithm? You can comment in the chat section. I just want to see. Just say yes in the chat section if you guys have heard about YOLO algorithm. Okay, I got, okay, no, yes. Okay, most of you haven't heard of it. I can see no more. Some of you have said yes. Okay, so YOLO is like a state-of-art object detection algorithm that is currently being used. And if you guys don't know about it, that's okay. We're gonna see it here also. The point what I wanted to keep it here is most of the student, those who are starting with their journey in this area of object detection, what they do is they directly follow some YouTubers and directly do this application or implementation of algorithms. But that's not what I want a person to do. He should be aware of what was going in the past and how the things changed to YOLO algorithm. So for those who don't know about, okay, for those who don't know about it, just get to know that YOLO algorithm is a state-of-the-art architecture algorithm which is used for object detection, and we'll come towards it. And the aim of today's presentation is to make you aware of what was before it, what was before it that motivated towards YOLO algorithm. We should be aware of it. Okay, someone is saying no audio. Can you hear me, guys? Comment in the chat section. I guess I'm audible to all. Okay, Vinay Kumar, please check your mic or something. Okay, I'm audible. So yeah, I guess you all got what the point of today's section is. Today's session is we want to see what was previous to YOLO algorithm, so that if you are someone who want to do research into it, or you can be someone who will contribute towards this kind of algorithms and which will bring out something new to people. Okay, we don't want to be a copy person. We want to be someone who will contribute to this community. I'm happy that many of you are here. Let's proceed. So what do we have with us today? We want to see where object detection is. Now, if I ask you guys, like, tell me where do you use object detection in your normal life, you might not be able to tell me 10 even examples, okay? This happens. Okay, but we are going to see 10 different examples, and I will make you realize what is the importance of object detection. Next thing is we're going to see what is the map of object detection algorithms, and this will make you realize how important it is to study what was previous to YOLO algorithm and all. We'll see basic terminologies like people are confused with classification, localization, detection, and segmentation terminologies. So these are very easy terminologies. We'll see those things first. After that, we'll go to some of the shallow algorithms, which are not kind of deep neural network examples, which are basically some classical CV2 algorithms like shift and hog. We'll see behind what is the intuition behind this kind of classical algorithms and why do people use them. After that, we'll deep dive into deep neural networks and we'll see what is the need of it, whether there is a need or whether there is some disadvantage going to deep neural networks. After that, I wanted you guys to know about this kind of concepts like sliding window, image pyramid, bounding box, because this kind of concept will always come in front whenever you're gonna read some papers. Let's say if you are someone who is into his final year and want to have his project, so he is going to study some papers. Like in those papers, you will get to see these kind of terminologies, and you should be aware of it. Next thing is we'll be looking deep into RCNN families. What is RCNN? What is fast RCNN? After that, we'll see about what is YOLO algorithm. In that also we should know about non-max suppression. What is IOU? What is MPA? So these are the things we're gonna study today. And let's start with it. Let's see what are different kind of applications of object detection. So this is one of the example that I have come across, automated insurance claim. Okay, someone asked, like, can we go through a mask RCNN? Actually, practically, it is not possible today into like taking all this algorithm at a time, but we'll see in the next classes, okay? But for now, let's let's focus on the current slides, okay? What do we have? Automated insurance claim. So what happens is nowadays people like insurance companies, they are trying to replace people with this automated algorithms, which will find out what is the cost incurred for the accident and that much only to be repaid for the customer. Because it may happen that the person is biased towards the customer and that company will not want that thing, right? So this kind of thing has been going on. People are doing research into it. So you can see how it is detecting a bumper, how it is detecting the mud guard, which is damaged. In the second image, you can see how confident it is to see whether it is a scratch. whether it is a dent, whether it is a color loss, right? So this is one of the biggest, one of the thing which people are researching and doing, implementing things. Next thing we can see is traffic monitoring. Okay, this is one of the thing you might have come across, like you might have heard smart traffic monitoring, smart traffic management. So what they do is they use those CCTV cameras, those are used in the traffic light you have seen, right? So those kind of thing are used, and they can detect like which area is having more amount of someone has unmuted. Do anyone have any question, guys? Okay. So this kind of things has been used, and people see like the governance see that where in which path do we have the traffic, and like that they will open the traffic lights. So this is one of the thing you might have heard of, and many of the people in their BTechs try to do this thing also. Next thing what we can see is, okay, in the field of medical science, this has been extensively used for detecting tumors and all. You can see this is a MRI image of brain and all, and you can see there it is able to detect where the cancerous cell is, and it is able to build a box around it, right? So this can be a very much time saving thing for a doctor as well. And yeah, next thing we can see, and also in field of medical science, someone is doing for detecting mitochondria in the images, right? They are detecting for lung infection as well. So more of the studies are going into detection of cancerous cells and all. So you can read about that as well. Next thing is, you can see in autonomous drones as well. You might have seen in YouTube videos also, the guy is using drone. You can see in the first video he's throwing the drone and drone is following him, right? And the second one, you can see the person is cycling in somewhere in the forest or somewhere like that, and the drone is following him, right? Yeah, so following that person, or following that the person who is cycling the bike will definitely require detection, right? He will have to, that drone has to detect the person and he has to follow him. So this kind of technology, of course, use object detection. Next thing you can see is people do use this thing for surveillance purpose as well. So this is kind of a smart surveillance thing what people do. Next thing you can see is player tracking. So nowadays this big teams, they do hire some experts who are tracking this players, and they do track how they are playing, what they are weak at, what they can be improved on. So this kind of studies, for that also they need to do real-time object monitoring. This object can be the player as well, right? Next thing is, you can see in industries as well. So this is one of the example that I saw. So you can see this is one of the industry application in which the industry is for that glass manufacturing, and you can see that if there is any dent, it is able to detect that dent, draw a bounding box around it, and it can tell you how much confident it is to tell you that it is a dent, or it is an aberration, or it is a burr. So this kind of thing are very much useful in industry. If this kind of thing goes into person's side when it buys this product, the company don't want to defame themselves, right? And they want to remove this product as soon as possible from their assembly line. So this can be automated using detection techniques as well. Okay, this thing also, you can see there one more example. You can see seal breakage, and they don't want this default or say faulty products to go into a market, right? So they want to remove it as soon as possible, and they can't keep they can't hire a person to watch whether the cap is proper or not. So these algorithms can find this thing, and with like more accuracy than a person, you can say. The second one, you can see the helmet detection. So that can also be done whether a person is wearing his helmet or not, whether he's wearing proper equipments or not. But this is very much useful in that dangerous kind of environments in big industries, right? And next thing you can see here, we can also detect the barcode as well. If some box is not having that barcode on it, so it can detect it. So you can see there are many other applications of it, and these are extensively used in today's industry. Next thing, you can see this helmet and license plate detection as well. So they do have these things nowadays. When I was residing in Pune, so there also they have installed this kind of thing. The RTO has this thing, so they can detect whether you are wearing helmet or not. they can detect your plate number and they can directly find you. They don't need to catch you. So this kind of applications are also there. Next thing is you can yourself see in your cell phones as well. Face ID detection, right? Face identification, you can see face detection, face identification, and some of the people do this thing. They do this kind of projects as well, like facial expression recognition. Now you will say like this kind of thing should be able to be done using classification, but remember this thing, through classification as well, you might not get that much confidence. Like if you just crop the face and then put it to the classification, that's more, the algorithm will perform more confidently instead of a picture which is having background as well. This background might act as a noise for it. Instead of it, you should be able to crop the face of a person and then provide it to your classification. So yeah, next thing you can see in Apple as well, some of the last updates, you can see they have introduced this animoji, in which the emoji can track your facial expression and it can imitate them. So Apple also uses this, and few of you who might have attended my previous lecture on CNN, introduction to CNN, there also we have seen some of the application where Apple has used like the background blurring, making the background black. So this kind of thing can also be used, done using object detection. They should be able to detect the object. That's after that only they will be able to process anything, right? In this scenario also, they are able to first of all detect the face, and after that they are tracking your facial landmarks, and that's how they are able to imitate an emoji according to your facial expression. So these were all the examples that I might have like you should be knowing about. You should be knowing these are the applications around you in industry, in medical field, like in your cell phones. Okay, some of you might be having that feature in your cell phone which tells you the age and all, right? For that, the phone first has to detect your face. So that all thing come under this detection algorithms. Let's see what is the importance of looking towards the evolution part. So you can see this is a map. Now what this map tells you, okay, if don't get confused if you don't know anything about it right now, but for now just see what and all things are there. There is convolution. So people who are coming from convolution neural network, first of all, when the convolution was introduced, after that only AlexNet came in the picture, right? AlexNet became famous because it's used convolution neural network inside of it, got a good accuracy, and that got famous. Then the above are all other algorithms that got famous. Like you have the technique like color detection, you have edge detection, you have concept like superpixels, histogram, corner detection, and gradients. Using these all things, all other things got invented. So if you see like SIFT, the SIFT and HOG are both very famous in CV2 library. People do know about it. So before introduction of SIFT and HOG, there was invention of histogram method, corner detection, and gradient. Those lead to the introduction of SIFT, and HOG was because of gradient. And that's how then next come to BOW, which is also known as bag of visual words. And then HOG also helped us to get into deformable parts model. And BOW comes to spatial pyramid matching. And this is how the web it is. It's not a straight path, okay? There are many other things which were invented before this RCNN family. Okay, some of you might not have heard about RCNN as well. So RCNN is also very famous for object detection kind of things, but it's not like someone directly invented faster RCNN. Before that, there were huge efforts in efforts in building out this kind of algorithms, and they mapped together these things, and they got the follow-up till faster RCNN. After that, you got other things also. RetinaNet is there. You have SSDA. What do we have? We have YOLO algorithms as well. Now we have various versions of YOLO algorithms, but this all comes from this only. You should be aware of convolution. You should be aware of this kind of techniques which lead to their formation. So now let's be clear with some of the terminologies. What is object classification, object localization, object detection, segmentation? So if you have some architecture which is able to tell you whether the given image is a cat or a dog, it is known as the task of classification. If you have a network or if you have an algorithm which can tell you where that cat or dog is in the image, it is known as localization. I hope you got it. If you don't have bounding boxes, you just have the labels to them, then it is classification. If you have the bounding box, then it is known as localization. If you can do the both of the thing, then you can say it is your object detection. Then what do we have? Object segmentation. For object segmentation, we classify each and every pixel. Okay, if the pixel is belonging to the cat, it will get different color. If the picture is not, if the pixel is not belonging to the cat, it will get different color. So this is how the object segmentation is. It's very simple terminologies, guys. If you are able to differentiate between them, it's classification. If you can draw a bounding box around it, it's known as localization. If you can have that bounding box as well as cat as well bounding box as well as the label for a detection, then we have segmentation as well, in which we classify each and every pixel according to their classes. Okay, I hope you guys I hope you all guys get it. Okay, let's start with the problem of detection. Let's say we have this original image which is to the left, and we have another image which is a cropped version of it. And I ask you, how will you find out whether this second image, which is a cropped image, is actually the first image or a part of the first image? So if I ask you this image, is it this image? So like, do you have any idea? Can I see in the comment section how will you proceed? Don't go for any algorithm, but just tell me, what will you do? It's segment of image, right? But you can say it, but how will algorithm will, how a computer will see it? How will it know whether this image is a part of this image? Just think of it like, if you think simply, what you can do is you just take this image, you slide it over to, like, you can just take a portion of the original image and just this kind of portion, and you can see whether it is matching or not. If it isn't matching, then just slide it to somewhat right, then again to the right, then again to the right, just slightly to the right, and more and more and more, and you can see that this is matching. And you will say that this image is a part of this image. That means you have detected something, right? You have seen that this image actually belongs to this image, right? But let's say if the problem is not that simple, I have another image which is kind of zoomed as well as cropped as well as rotated image. What will you do? Will you take some portion of this image and then zoom it, then crop it, then rotate it, then again you will slide your window somewhere to the right, then again you will take some portion of the image, then zoom it, then crop it, then rotate it? Now it is too much computational, guys. If you are even into programming, if you can think of it, how much computational this thing can be, just sliding this window and checking whether each of the pixels belong to the same or not, whether they are same or not. And now for now, if I'm moving this thing, I'm like jumping from 10 to 20 pixels at each time. But when you are doing this thing in the computer way, you have to go one pixel each. This is not a good way to do this thing, right? And you get into trouble when the thing is more complicated, like zoom, crop, rotated. Imagine if I change the contrast as well, you won't be able to match the pixel values as well. Okay, and this is what the problem is. What should we do? What can we do? We need to have some intelligence into it for detection. What can we do? So let's move the next thing. What we can do is let's think, like, let's take some of the boxes from the image. Like like you can see, we have the yellow boxes on yellow color boxes on the image. We can just take those boxes, and maybe we could compare these boxes with the image that is given. And if these boxes matches, then maybe we can see that the given image is just like this image. But again, I think this is more computational. This many boxes. How many boxes do we have here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 70. Oh man. So we'll compare 70 boxes. Now that also I think is very computational. What intelligence again you can have? Okay. For answering that thing, let's go to one simple exercise that I want you to answer me. So let's say you have this image, you have 6 other small images given, that is A, B, C, D, E, F. And I want you to tell me which this small images, where do they belong to? Okay, I can see some of the responses. Someone is saying train and all, but we don't want to go into that complexities. for now, we are considering that we are just a newbie into it, and we want to see whether with some simple logic can we do it. So tell me, we have this A, B, C, D, E, F images, and so yeah, we can see. Okay, so you can see you can make a difference, like this E belongs to somewhere like here, F belongs to somewhere like here, C might be coming from here, somewhere from here, and might be D coming from here. And what about A and B? Might be you will say B comes from here, but where exactly from? Might be from here, it can be from here, it can be from here. And A, A may be from here, maybe from here, but if you see the density, if you see the color, you might say that it comes from the upper right corner. It's more darker there, but where from? Like here, or somewhere from here, somewhere from here. So why is it like we are not able to differentiate this A, B, and we are very much comfortable with differentiating C, E, D, F? Okay, I can see some of the responses. Now tell me something that I want to put light on. What I want to tell you. What do this exercise tell you? You're not able to tell properly where exactly A and B comes from, but right after you see E and F, you can definitely tell that E is from the left corner of the building, F is from the right corner of the left building. Okay, I will tell you the answer. The thing is, those are corners. Okay, this is how our visual system works. We are not that much good into seeing the planes. We are good into seeing corners as well as edges, and that is what we'll take advantage of. We want to take advantage of edges and corners. So if we again, if you're not getting me, let's go to another example. Let's say if you have this first block, blue color block, you have a red colored box into it, and you just shift it to the left, right, and shift to the down. Is there any information inside of it? I guess no. There is none of the information into it. And if you see the same example, what I want to tell you is A and B. If you take it here, somewhere on the top corner, and if you shift it slightly to the right, slightly to the left, it doesn't give you any information. That's why that information is not with you, and that's why you're not able to differentiate those planes, those examples. But if you see the second example over here, if you see this where my cursor is, you have the red box, and if you slightly shift it to the down or slightly to the up, you will have different portions of the blue color into your yellow boxes, right? And this is the information, this is the actual information that your brain interprets. Okay, and if you see to the this this age, there is one red box, and that box, if you move to the left, move to the right, you will definitely get some difference, and that is what information for your brain. If you now the other thing is, if you move this box in the direction of the age, you won't be able to get any information. Take this example. If you have this red color box, if you move it in the direction of the age, you will see the same thing. It's not information for your brain. You want something different into that box. Just like you're doing up and down for this box, you can't have the information when you're moving in the direction of the edges. But what about corners? Let's say this is a corner, and you have this red box that's overlapped. Okay, manage it. And we have this yellow boxes. So yellow color boxes, if you do it up or down, slightly to the right, slightly to the left, you will definitely have separate portions into them, right? And that's what information is. So what we can say is corners are more useful to extract out information. After that, we can say edges, but in edges also, if you move along the edge, you won't be able to interpret any of the information out of it. And in the planes, don't talk about it. That's not of any use for now. So we'll make use of this. So where do we start from? We started like we'll take an image and we'll compare it pixel by pixel. Okay, guys, can you hear me? Because I'm getting the message that my internet connection is poor.
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So where are we? We saw that comparing pixel wise pixel wasn't good enough. Why? Because if we do the zooming of the image and if we do cropping, if we do like changing of the color and contrast, then it won't be of any use. But suppose if we are able to find out the edges and corners, Those will be more informative thing that we saw out of these two practices. Okay, out of these two exercises. Now let's go back to that image again. Let's say you have an algorithm which provides you with these boxes intelligently. It provided with you with some boxes. You can see blue color. Blue color, I guess those are edges. Red color, I guess those are planes, and green color are actually corners. Now you have the choice. You know corners are more important than edges. So to reduce your computation, what you can do is you can remove out these red color boxes. And what do you have now? You have just the green color boxes left. And what do they represent? They represent corners. If you see it properly, just see the eye is the corner of eye, the corner of mouth, the corner of this design on her sweater, the flower petal. They have the corners into them. Now these are very much unique to this image. Now if someone tells you that I'm giving an image like this, now tell me whether this belongs to here. You don't have to take this image again and slide it over again and again. What you can do is again have this corner detection algorithm applied for this image as well. It will give you this kind of boxes again. Just compare these boxes. No, how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8. Just look for the 7 boxes. If they are same, that means this is the same person, right? Okay, it might happen this is a cropped version of this image, so this box is not there. But after all, you have the control over it. Okay, you can set the threshold. At least you are getting 6 or 7 boxes out of them, 6 boxes or something like that. So you can have that thing. Okay, that will define your accuracy as well for that algorithm. For now, what do we get? So we decided to slide over the image, but we saw that that is too much computational. After that, we saw that if you want to extract out information out of any image, then what is useful? Useful is corner and edges. But someone asks you what is more, better, which is the best one? That's corner. So you want to find out these corners. For that, you have corner detection algorithms. Using that, you can do it. But again, there is some limitation. Just think of it. Just write in the comment section or chat section. Just tell me what do you think is missing here? What can go wrong with this technique? Come on, think of it. We are detecting edges. Now what can go wrong with it? Okay, someone is asking how to find corners in sky pick blue. We don't need to find that blue. That's what I'm telling. That was the exercise to tell you that that wasn't any information part from that image. If you are given the same image, okay, we don't have any responses. I think people are thinking of it. Okay, let me tell you. What if the image is zoomed? Okay, this is the cropped image. Okay, I didn't tell you. I think I did. You guys should have been recognized it. This is the cropped image of the first image, and that's why your corner are detected. What if the situation is like this? Just look at this situation. Let's say the first thing. Where is my cursor? Okay, this thing. This thing is from your first image. You ran your corner detection algorithm on it, and your corner detection algorithm tell you that this is a corner. Okay, and then what happened is someone gave you a zoomed image of it. Now this corner becomes something like this. Now you can see the corner detection algorithm tells you that this is an edge, this is an edge, and this is an corner. And if you compare them, you won't be finding the similarities, right? This won't be equal to this thing. Now things have gone wrong, right? What you started with, you said corner detection algorithm will help you out, but what if it is zoomed? Though it will be like it will perform well even if you change the colors and all, like if you change the contrast and brightness. But what if it is zoomed? It won't help you out, right? So what you can do now, you want something else. Okay, now we want something else. What is that? Sliding didn't work for us. Corners didn't work for us, not that well if the image is zoomed. And the next option we have is feature descriptors. So what is feature descriptors? This thing is like something which will change whole scenario. Okay. This is the base of your CV2. Now, most of you might have heard about CV2 library. It is a very, very famous library, computer vision library, in which you have some supports of this kind of algorithms, which are known as feature descriptor algorithms, which will find out something which will be so useful that you can't even imagine, which shaped our future, like where we are right now. Okay, so what is this thing? What this will do is it will take small image patches. Image patches is what, say your algorithm detected this patch, right? Now what it will do is it will take that patch, it will do some mathematical operation, and it will transform it into something known as feature vector. If someone of you are from CNNs or convolutional neural networks, you might be aware of what is feature vector. Given an image, if you pass it through the algorithm, it will provide you with some vector, a 1D vector, which is too much useful, which brings out the information of that image. Okay, and that's what these feature descriptors are used for. It won't make any sense to look it with our naked eyes. It won't be making any sense for us, but it will make sense for something which is known as SVM. Now, if you are not aware of SVM, I will highly suggest you learn about SVM. SVM is very much useful into machine learning area, and it is used for finding out such kind of pattern recognition things. So what is the task now we are framing is, we'll use this feature descriptor, something known as feature descriptor, which will give us feature vectors. We'll feed this feature vector to SVM, which is known, which is also abbreviated as support vector machine. And the support vector machine will tell us what is whether this what is this object is. Okay, is it the same object? Is it a dog? Is it a cat, or all? That thing will be managed with support vector machine, but the feature descriptor will find out the important features out of that image, whichever is feed to it. So let's move further to it. Okay, do remember these all things. So what and all we got wrong. One slide question to you guys. What do you think was the year when corner detection algorithms were invented? Just think of it. How old can this technology be? We have seen corner detection, no? So what do you think, in which year might this like approximately this thing might be old of? 1990 someone has written, and that's good, right? Even I have written this thing into the slide, 1988. So you can find some papers which tell you like it's from 1980s, dude. So just imagine how sacred it is, right? You should be like studying regarding it. Start to know about this kind of algorithms. Okay, these are like backbones of our object detection algorithms. They have supported us. After that, we have some advancements as well, and those are like feature descriptors. So let's move on to feature descriptor. What are this? So one of them is known as SIFT, scale invariant feature transform. Now we are not going to go into equations and all those kind of stuff. I want you guys to be aware of it. So I'm going to tell you, I want to make you guys aware of these things. Like this kind of things also exist. Okay. Okay, so we had this algorithms of corner detection like 1988, right? And now in 2004, somewhere close to it, someone introduced us with SIFT, scale invariant feature transform. Now, what is the specialty of it? Just look at this first example. Just look at towards my cursor. This is an image, and this is the same object you can see. Just the background is different, orientation is different, as well as contrast is different. Everything is different, I can say. Just the object is same. But the SIFT algorithm is able to find out the features out of that first image and is able to match with the features of the second image, even though it is rotated, even though the color is changed, even though the background is changed. It can match 5 out of 3 features out of it, right? Maybe the 2 are not detected because they are too small for the second image to detect. But this is how robust SIFT is. SIFT is able to nullify those rotation, nullify those background, and all the scaling things. The second example, how strong SIFT is, I want to make you guys realize of is, just see this example. These are 2 images, separate images. The first image is somewhat like zoom out image, and the second image is zoomed in image. You can see color difference as well. Color of background is different. You can see a shadow over here, right? A shadow here. The shadow is not present over here. Now look at the beauty of this SIFT algorithm. It is able to match them. Even it is able to draw the lines and match them together. How strong it is, right? even though the background is different, even though the zooming scale is different. Okay, so guys, unmute only if you have some doubt. Yeah, so what we were looking at is shift, how good it is, right? We have seen the problems with shifting, we have seen the problems with corner detection. Now this algorithms comes in 2004 and we change whole thing. It is invariant to all this kind of thing, invariant to rotation, invariant to scaling, invariant to background, invariant to image brightness and contrast. So I will highly appreciate if you guys go and read about this thing. This is very much good to know. These are very extensively used using CV2 library. You have support over there also. If you want to see, you can go through some YouTube videos and learn how to use it and practically use it. Okay, let's move for next thing. Okay, look at this also, this application of SIFT. You have seen the first image. You can see the image of a box which is at different orientation, and second image which is at different area. Okay, we have some comment whether shift algorithm. Okay, we'll look at the comment afterwards. Let's focus on the PPTs first. Okay, so we can see that the first image having a different orientation of the box, and second image having the straight orientation. You can see how it is able to match them, right? How strong it is to match them out, even if the scale is different, even if the orientation is different. This is all because of the one thing, that is corner detection, as well as robustness to the scaling thing, right? Robustness to change in the contrast and color. Okay, so what next? Next is HOG, the histogram of oriented gradients. Guys, this is also another thing which is which you might be which I want you guys to know about. If you're gonna study, do study about SIFT. After that, come to HOG. HOG is very much famous. Now this thing also makes use of that only. It is something like the maths is different, but at the end it is also trying to find out edges as well, edges and corners. So what it makes use of is it finds out the magnitude of gradient, as well as finds out the direction in which that gradient is. So let's take an example. Just see over it. Let's say we have this black color which is having value 0, and we have this gray color which is having 50, white color having 100, and this is slightly to the gray side which is 25. Now how will you find the gradients? What does gradient means here? I want you to have the intuitive understanding behind it. We won't be going to the equation. I don't want to bore you out, you guys. Let's go inside of it. So what is it? So let's say we have the direction in this side. You have a value 0 and you have value 100. So what will your gradient be? Your gradient will be 100. If you have something, your sliding window here, and if you move it slightly to the right, slightly to the left, you won't be getting any gradient. It will be 0. Similarly, when your box is here, it will be 0. Similarly, when it is here, it is 0. And if it is inclined, if you're finding a gradient 40 to 45 degree over here, it will be also nothing. So if it is like this angle, which is 90 degree, which is perpendicular, and if you move from the darker section to the whiter section, you can see the gradient is 100, right? And this is something which is telling you ages, right? Here we don't have any age, we have an age here. So this is how HOG works. It also finds out the same thing, ages as well as your corners, but something in different way. You have to go through the maths of it. And if you want to understand more about it, you can, whenever I share this PPT, or will drop this links as well after this lecture. So this is what the histogram of oriented gradient is. It will also find out edges and corners only. So if you want to have, if you want to see the example of it, let's say this is an image, and if you pass through the algorithm, what it will detect is edges. So how is it detecting edges, if you say? So let's say if this is a corner, right? And this is also a corner. If you see, this is a corner, this is a corner. If you see its representation after HOG, you can see this thing different than this thing, right? This is different than this. If you see this age and this age, this is also different. And so the representation is also in different orientation. So something is there, right? Some information is there which is telling you orientation, like which is telling you ages, which is telling you corners as well. these two corners are different corners, and that's why you have different representation for them as well. So all the things boil down to one thing. You want edges as well as corners, and those will be feature descriptors for you. After you get this feature descriptor, you can have a use of SVM. Of course, through your eyes, you are able to differentiate it, but for a computer, it won't make any sense. For that famous algorithm known as SVM, it will be used for it. And if you want to see one more example of it, you can see this man. If you do this hawk kind of thing on it, you will see that it is able to extract out the edges out of it, right? And different type of edges, different type of corners are getting different type of notation for it, right? Okay, and when was this invented? This was like 2005. So where we started 18 something, we came to 2002, then we came to 2005. Okay, now moving forward. Okay, this is the assembly. What you have an image, pass it through Hawk feature detector, it will detect out the feature, and now you have to provide it with the SVM detector. Now people who are not aware of SVM, do take a note of it. You guys should read about SVM. It's very famous in machine learning area. Okay. And if you guys want to read about more about it, these are the links. You will be having it. Okay, so over and all, what do we have? We have an image. We want feature out of it. What kind of feature is that? That is a corner, that is the edge, that who will extract them out for you? That is Hog, Sift, or something, some other algorithms like them. So you have Har, Cascade, some other algorithms are also there, which will help you out to extract out these features. You just flatten them out and you just provide it to the SVM support vector machine, and it will do the helpful things for you for the classification purpose. Okay, so what do we have now? We have seen some basic ideologies which could be useful for detection of an object in an image, and we got to know what are the things behind it. We started with sliding, and we came to edges and corners, and we came to know that there are some algorithms which will be helpful for you to extract out this kind of features. Those will be fed to SVM, and SVM will do the required thing for you for the classification purpose. Now let's see the whole scene. Okay, the whole scene where deep learning came and where these guys were. So if you can see here, there's my cursor. Okay, so this was year 2010, this was year 2011. So this was the competition. So this is whatever you can see, ILSBRC, this is the name of data set. Don't get confused with it. Just imagine this is the year 2010, this is the year 2011, and there was something on which it was used to be tested on, this kind of algorithm, how good they are. So what happened was, this 28.2 take is as error rate. So this was the error rate if you guys use Sift, Hog, or something known as Surf, ORB, or Voila Jones, or Har Cascade kind of things for extracting the features and passing them to SVM for your classification kind of thing. So the error rate which you were incurring was 28.2 or 25.8, something like that. Now the change came where deep neural networks started to come into picture. So AlexNet. So things for convolutional neural networks come into picture, like come into light for all the research people when AlexNet got popular. And why it got popular, you guys know, right? Convolutional operation, what it supports. So using convolution operation, we got this convolutional neural networks, and AlexNet was one of them who was using it, and he got pretty much good accuracy. You can see the jump, right? 25 from 25 it came to 16, something like 9% drop, right? And this is why the people got excited about it. This is why they started to see towards it. What is deep learning? What is it? And slowly in 2013 we got one more network which was 8 layers. Then we got something like VGG 16, VGG 19. This kind of architectures came into the picture, which were like 19 layers deep, and the error rate again came down to 7.5. Don't get confused with all this notations. Okay, I will tell you guys what these are, but for now just follow me. So we had an error rate of something close to 28.2, which dropped to something like small, but it wasn't that much exciting. But when it dropped by 9%, people got excited. Now let's see what is this deep neural networks, why they are performing this good. And when we come to 2015, So ResNet was there and it performed so well, like where it started from 28.2, it came down to 3.57. So that's very minimal, right? And that's where that excites you to know what it is. How is the accuracy so good? This is the error rate. Okay, don't get confused with the accuracy. This is error rate. So it's amazing, right? But the layers were deep. Now it started with 8 layers and it went up to 152 layers. Now 152 layers that's why it's known as deep network. Okay, and that's where the name come into the picture, deep neural networks. Now the problem is, what should you go for? Whether should you go for a classical CV2 approach, which is your sift and hog, which extracts out the corners and which help you out for classification, or should you go for this kind of deep networks? They are giving you pretty much good accuracy, but what is the thing that that might be disadvantage with it? So the first thing that comes into the picture is size. So okay, if you go for something like this sift and hop feature detector, you might end up with an algorithm which will just take 4 KB of size. And if you go for something like this deep network, like ResNet network, which was introduced in 2015, so that took like 152 layers, and for 152 layers, it used to take 25 million parameters. Now, if you want to save this 25 million parameters, it takes 100 MB size. And to train this kind of algorithms, you need GPU, and that is heavily computational. And what if you want to deploy this thing into your edge devices? Now, what is edge device? Edge device can be your cell phone as well, or you can say your computer. Now, you can't have this big size for application into your cell phones, right? 100 MB and all. Like you want to reduce it, right? You want a good accuracy as well as you don't want to take it this much amount of size. So if your application is something which is not that much computational, which does not require that much computation, and your edge device is not that much computationally good, you can go for classical CV2 approaches. Yes, error rate is more, but that is manageable with the size. Yeah, you can see 100 MB, and what is 4 KB, right? It's too much less. So it's your thing. Again, it depends on your application. Okay. The one thing that you will be compromising is the accuracy. Now, one more thing, which is disadvantage with this deep neural networks are, there is famous saying, what you think your model is learning and what your model actually learned, it's not same. Okay, so if you think your model is learning something, it won't be same what do you think. Okay, it won't be like you think the model is thinking this learning this thing, and it will be learning that thing. There was one of the study, so I will take that example. There was one study in which they want to classify whether a tank is in forest or whether the tank is in open area. They created the data set. They had 100 images for tank which was in the forest, and they had 100 images of tank which was in open area. Now they tested it on your testing data, and they got very much good accuracy. Now they were amazed with it, like how can it perform so well? Now they collected again some more data and they tested on it. Now what the thing came into picture is the deep neural network had nothing to do with the structure of a tank. That is my cursor. Okay, so you can see this is the structure of a tank, right? But the network didn't learn it. What it learned was just to see whether it is a sunny day or whether it is a cloudy day. Now, come on, you don't want it to happen, right, with you. So you should be aware of all these kind of things a network can go bad with. There's one more example in which there was one study to detect whether the cell is, you have this study, right? Detection, whether it is a malignant or benign cancer cell detection. So in that, there was one study in which they had two samples, two different types, malignant and benign. And in malignant, they used to have a scale which used to tell how much is the length of that tumor, how much is the size of the tumor. And in benign one, they didn't had it. And they trained the model, and they were also getting a good accuracy. They again got some more data and they tested on it. And what they came to know is the model didn't learn anything about this cells. It just learned whether there is a scale or not. If it is having a scale, it was classified as malignant, and if it is not, then benign. So come on, you don't want it to happen, right? So if you're going for this kind of architecture, deep architecture, you should be aware of this kind of outcomes as well. It's not what you think the model is learning always. Okay, but contrast to that, if you come to this classical approaches, these are handmade feature extractors. You know what kind of features are being extracted out of that image. If you read more about this kind of Swift, Hog, and Har cascade kind of algorithms, you will come to know that the feature extractors are hand engineered. They are not kept on on luck. Okay, here you are on the luck whether the model is learning that or not. You have to do many iteration, you have to do many experiments to find out whether the model exactly learned what you wanted. So these are the two things which you have to keep into mind. If you go for deep networks, you don't know what they are learning. If you go for the this shallow kind of network, these are known as shallow networks. Okay, these classical CV2 networks are known as shallow networks, and because those are hand engineered, those will not be learning anything other than what you have engineered in your feature extractors. That's it. So it's your choice. Okay, let's move further. Okay, let me tell you what are different data sets available. Now, I hope most of you guys are aware of data set, what data set is. This is what your deep neural network will be trained on. Now we are done with classical approaches. Okay, now we'll be deep diving into deep learning approaches, and I will make you aware. I will try whatever I can tell you guys. So let's see what we have. So data set, what are the different data sets available for you if you guys invent some like new algorithm, and if you want to test on that, what you can do is, so there is one data set available as Pascal VOC. VOC abbreviated as Visual Object Classes. You have COCO data set as well, which is known as Common Object in Context. And you have ImageNet. Now, ImageNet competition is very famous. Most of you guys might have heard of it. Like AlexNet got famous from there only. Your VGG16 got famous from there only. So they participate in that kind of competition in which they have to like classify 1,000 different objects. They have two different data set as well. 200 is also there. So you can see in Pascal VOC, you have 20 different classes. In case of COCO, you have 80 different classes. Now, if you ask me which data set should you use for training your algorithm or your model, it's better not to go with ImageNet data set, because ImageNet data set do not have like multiple object in single image. Now, if you are building any object detection algorithm, you will want that in a frame, if multiple object comes, it should be able to detect them. But ImageNet dataset mostly contains images which have only single objects in them. So it's your choice, but most probably don't go for ImageNet dataset for training of object detection algorithm. After that, you have a choice for Pascal as well as COCO dataset. In COCO dataset, in Pascal dataset, you have 11,000 images. That's a small dataset, I will say, compared to what a COCO dataset, it has 330,000 something images. And in 11,530 images, you can see we have 27,450 reason of interest. Now, reason of interest is image might be having multiple objects inside it. So they might have annotated, or they might have created ground truth around those boxes, around those objects. So in total, 11,530 images, and that you will be getting 27,450 objects to learn from, and 20 different classes. And you have second choice for COCO dataset, which is a bigger dataset compared to Pascal, and which will be having 1.5 million object instances inside it. Total, this 330,000 images will be having 1.5 million object instances inside it, and 80 different classes. Now it's your choice what to go for, but I will suggest go for Pascal VOC first. Okay, go for Pascal VOC first. It's a small data set. If your algorithm perform well, then go for COCO data set. And we'll be looking forward for some paper outcomes related to these two data sets. We'll not be going for ImageNet because that isn't a data set you should be interested for training your object detection algorithm. Let's move further. Let me give you some examples from this data set. You can see here, right? You can see a Pascal data set, how it looks like. So you have an image and you have the bounding boxes around it. So these are the annotation that they have provided you. You can see, right? The people sitting, they are also, humans are also there. And what else do we have? Children, there is some bottle, I guess. So they have also down bounding box around it. We have chair as well. And they will also be having a label towards it, right? Let's see this COCO data set. So COCO data set is very good to use, go with. If you want to, Okay, if you want to explore this thing, Coco dataset, go for their website. It's very good website. You have the option to select what kind of objects you want in the images. Let's say you click on humans and dogs. Let's say here you click on humans and dogs. You will just get the images of human and dog. You can save them. Like you can see here one human is there. Here one dog is there. Human and again a dog. Human and again a dog. So Coco dataset is well maintained. If you want to go and if you want to have some specific objects into your images, you can have that option there. You might not have that option in this Pascal dataset. That's your choice. When you want to experiment with, you can go for it, or you can take whole dataset as well. Okay, now tell me. Now the question comes: what if you want to generate your own data? Like these are all the objects they have in their dataset, but what if the object you are searching for isn't here? So what you can do is that will be something known as manual task for you. You have to collect all the images, and there are some softwares known as softwares like Label MG. So this kind of softwares are there in the market. You can use this kind of softwares, and what you have to do is just you have to build a bounding box around this object, and it will itself find out whatever coordinates or whatever useful information is required for training your model. Just have to label it, whether it is a person, whether it is a cat, whether it is a dog. I guess someone has unmuted themselves. I'll mute them. Okay. So what I was telling you, it might happen that in some of the examples, I request all of you to keep your mic off. Okay. It might happen in some of the cases that whatever object you are having interest in, whatever algorithm you want to build for, that object might not be inside your data set, and you will yourself has to develop that data set. So in that case, you have support of this kind of softwares using which you can have this data set ready, and you can search for this Label MG software as well. Now that I have shown you something regarding this object detection field, you have seen what are the data set available. Two data set what I have told you, that is this Coco data set as well as Pascal data set. Now let's move further and let's deep dive into deep networks. We have seen the data set. Now let's see what are the architectures. This was our previous thing, right? There was an image, we used to extract out the features, then we used to pass it to the classifier, right? SVM, and then we used to have the bounding box. Now let's forget it. Now let's deep dive into deep networks. Now, how many of you are aware of classification task? Just write in the comment section, how many of you are aware of doing classification using convolutional neural networks? Or you might have attended my lecture last time. Okay, I can see yes from Sapna. Aware. So people are aware of it, right? What a classification task, how you can do it. So basically, I will repeat it. What do we have? Gupta is unaware of it. So let me tell you. So I will wrap it quickly. So you have an image of a cat. You have a network which is well trained, already trained on, or you can train them as well. So you have an AlexNet, or you can take another whatever transfer learning you want to do, AlexNet or BGG. You pass that image, you get some feature vectors or say feature maps. You convert them into 1D. After that, you have fully connected layers, and at the end, you have a softmax layer which will provide you with the confidences, whether what kind of image that is which you have passed to the network. So this was the simple classification task. Now, what do you want? We want that a box should also be there. How will you create a box around that image? You want a box as well. You just don't want to classify it, right? You want to localize it. How can you do that? So, okay, so here comes the bounding box concept. So already what we have an image. We provided it to CNNs. It used to give us some softmax score, and based on that, we used to make it belong to certain class. Now, what a simple thing you have to do is you have to have 4 different layers. Okay, don't go here. First, go here. So how will you create a bounding box? So this kind of bounding boxes you yourself has to create on your data set. Okay, it's not like it will automatically detect it. First of all, you have to train him where the bounding boxes are. So let's say if you have a box here, you can see here we have a box for cycle, we have a box for a boat as well, right? And how are they labeled? Let's say you have drawn a box here. What you can do is just extract out the x1, y1, x2, y2. You want this labels, okay? You want to create the data set which will be having this labels as well. Now, what the labels? I mean to say the coordinates. So you will be having this x1, y1 and this x2, y2, or you can take it differently. You can give x and y of the center of the box, give the x and y, and give the height and width of the box. So you have to make the architecture learn this thing. You have to tell him, you just don't have to do the classification kind of thing. Parallelly, what you want to do is you want to detect where the box should be and what are the coordinates. Once the algorithms provide you with this coordinates, you yourself can draw the box there. So algorithm is trained to provide you with this coordinates, and using simple CVT tools, you can have the box there. Now, but how will you do that? Earlier, we used to have a single layer, right? We used to have a single layer which used to give us the confidence. Now what you have to do is you just have to stack up 4 more layers parallelly. You can divide the network into 4 different things, okay? Go and study regarding it, but yes, things are there. You can do it like this way also. So what do we have here? So what will this first box belongs to? This will be x1, this will be y1, this will be x2, this will be y2. So you will be training your model. Parallelly, it will be doing classification, as well as it will be giving you the x1, y1, x2, y2 as well. So while training, you have to have this data. What are the coordinates for the input image which you are giving for training? And that you have to generate using whatever software tool we have seen, like label MG is there. Or if you are going for the data set, they will be having them in the data set. The data will be there, okay? Where are the bounding boxes? So, but we are not going inside of those kind of thing, but just let's see how simple way we can do it. For now, we have seen we can do it like this, okay? But how will the model will get trained? Here, we know about loss function, right? But what kind of loss will be here? So you can use here L2 loss. What a L2 loss will be? So let's take an example. Let's say we have an image and we have a boat over here. We have a coordinates that this will be 200 in x-axis. This will be 250. This will be 600, and this will be 400 for y2. What you can do is you just have to train your model. Let's say first of all your expected are 200, 250, 600, and 400 for respect to x1, y1, x2, y2. Now your model is not trained on it, but it is trying to train himself. So first of all, it might predict that it is 0, 0, 800, and 600. But yeah, we know it is wrong. How do you penalize the model? So if you know about classification, you have log loss function there. Here you have the squared loss, okay? What you can do is you just have to subtract the expected value and whatever is the predicted one, square it for all the 4 coordinates, x1, y1, x2, y2, and sum them all. And you will get an penalty value of this thing, right? You can see the figure. And the next thing, whenever the model gets penalized, it will try to predict it more accurately. And let's say in next step, you get 100, 150, 700, and 450. And again, you calculate those loss with respect to your expected outcomes, and you will again get the loss reduced. And these are the hypothetical values. So I didn't take it, I didn't scale it, just take it. These are some random values. So yeah, at the end, it might happen that your architecture will come close to your expected values and your loss will be 0. So what kind of loss we are using? We are using L2 loss here. So what will be we having? We'll be having a classification, as well as we'll be having this bounding box regressor kind of thing, and which will be having a loss, which is a L2 loss, using which the model will learn what should be where should be my bounding box, what should be the coordinates of whatever thing I have classified. Now, one more specialty about bounding boxes, if you train your architecture like that, let's say you have an image which is like half image of a car. So it will itself detect how much long the car may be. You can see the image is not having the full car inside of it, and the model is telling that it might be 500 in this direction and 300 in this direction. 300 is okay, it is able to find out from that image. But what about the length of the car? So it might have seen it in its training data that car is like something having this length. So it is taking that length. But let's say if you have another image which is giving some more information to the network, so it will be more accurate on it. It will take like 600. Now this seems to be good. Like this doesn't seem to be that well fitting. If you see this, it might be thinking it is something like this. Now this doesn't appear to be a good car. So yeah, and this is looking something good, right? Okay, so that's what I wanted to tell you. If you provide a small image, it won't be a good information for it, but though it will try for having the bounding box accordingly. If you provide a more information to it, it will be more accurate on that. Okay, so this is what we are up to. We have a classifier. Parallelly, we'll be having a bounding box regressor, which will be using L2 loss, and which will be doing both the things parallelly. This will be providing us with the confidence which class this image belongs to, and this arrangement of ours will tell us where the box should be drawn. Let's move further. Let's say we have multiple objects, like we are detecting for person, we are detecting for a board, we are detecting for a TV. Now, how will you decide where the box should be drawn? Of course, you will go through the confidence. You will see what confidence is more. The architecture says it's more confident that board is there with 95% accuracy, right? 95% confidence, it tells that it is a board, and you can take that thing and you can take the coordinates of that and you can just draw the bounding box around it. So you can decide on the confidence. It says there is a person, it detects that here a person is there, here a TV is there, but no need to have those boxes there, right? Why to have those boxes there if the confidence itself is less? Better to decide the threshold on it, that if it goes above 90%, then we'll draw a bounding box around it. So this is some kind of thing, some kind of arrangement that we are doing right now. So I hope you guys are getting it right. Where did we start from? We had a simple classifier. We decided to add some more layers which will help us out to train a model on x1, y1, x2, y2, and we'll train it using L2 loss, and we'll be having confidence as well as the bounding boxes, and whichever confidence is more, accordingly we'll label it. I mean to say, we'll draw a bounding box around it. Now we have one difficulty. Let's say you have an image of a cat. This is an image of a cat. Now, how do we provide input to a CNN? Now, if you are from the CNN background, if you know about it, we have a fixed size of input for CNNs. You can't input any kind of size. Whenever you define your CNN, the input sizes you have to keep the fixed. If you have to keep it fixed. So if the image is like this, you will manage to do it like this, and you will provide like whatever specific dimension you have decided with CNN. That dimension you will take it, and then you will feed it to CNN. What if I have? Let's jump into second scenario. Let's say in a single image you have two different objects. So you might think like, let's divide this image into two and feed it separately, and after whatever outcome we get, we'll stitch this image together. So we might get a bounding box around this cat, and we might get the bounding box around this cat, and then we'll concat them again together, and voila, we got the output, right? But think of it, it can get complicated, right? Let's take example of this thing. Just look at it. We have multiple objects over here, cats to detect, but where should I draw the boundary? Here I said I will draw a boundary in the middle, but how will you provide an intelligence to a software or to an algorithm to detect where should you draw the boundary? Whether should I draw it here, 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 or where should I draw? Is there any particular way that I come to know that where should my boundary be? Because this algorithm, this will detect only one image. What should I do? CNN, what should I do in that? Okay, so neither do I know the number of objects nor the location of the objects. So what can I do? Okay, now comes the scene of sliding windows. So sliding windows were something which were used in the initial era. So what they were used to do is, they used to consider a simple window and they used to slide it across the image. So you can see the sliding window over here, then the sliding window shift towards the right, then it goes till the right portion, then it comes to down, and again it repeats the same procedure till it reaches to the end. I didn't take all the all the possibilities. Just imagine it. There will be a window which will be going through all the pixels. Now it might find an object here and you will be able to detect it. It might not find object somewhere, that's not of our interest, but somewhere we might be able to get an object, might be here in this window, in this window. So eventually when this window will be sliding, it will be taking some objects into it and will be able to get those objects. So you might be thinking now a problem is solved, but think of it, how much computational it will be. You will be sliding the window again and again, and you will be feeding it to CNN networks. Now CNN network itself, just imagine how many parameters it has and how much computation it will have to do. That's another point. And let's take another point into consideration. Let's say you have an image which is not coming into that window itself. Let's say, just take an example of this man. Now this is your size of a window. Now look at this window, whether it is taking consideration of a whole man, because the man isn't of size of this, right? Let me change the color. You can see the man is something like this much length. Okay, don't go towards that ground truths. Those are ground truth. Yellow color are the ground truth. Just look at this red boxes. Whether this red box will be able to take this whole man into consideration? No, right? It won't be able to take that whole man into single window, and hence our model will not be able to draw a bounding box around it. What you can do is, now comes the famous thing which is known as image pyramid. What you can do is, you have to scale down your image itself. Just scale down your image to some specific sizes. Smaller and smaller the image gets, more and more the image gets into the window. So you can see we have kept the size of the window as constant, and you are able to get a whole man into that picture, a whole man into that window at once, right? And at the end, you might be able to detect the man, and you can get the better detection. So this is what one should be knowing about. Whenever you're gonna read some papers on object detection algorithms, definitely you will be coming across this kind of things as well. So this is the concept of image pyramid. Now you can see that we have scaled the image like 4 times, but there are papers, they have the specific resolution as well, that what size they have reduced it to. So here I've shown 4, but some of the papers, they go for 6 variations as well. And you can see if the object is smaller, that will be coming inside your window, and hence in the first resolution, you might be able to detect a smaller object. And as soon as far like as you go inside of it, like reducing the image dimension and keeping your window constant, you will be able to detect a larger object, just like this man and this bicycle. Okay, so you got the idea of sliding windows. We want to detect multiple objects. We didn't have the idea of where the objects can be, how many the objects can be. Next thing, the hindrance was the scale of the object. It might be a small object or it might be a large object. It might happen that in a single window, both of the things might not come. And that's why you want to go for image pyramid. I hope you got the importance of image pyramid, what they are and how they can be magical in this kind of algorithms. So we'll make use of this thing as well. So what we'll be doing is, we'll be having one sliding window. And what else we'll be doing is, we'll be taking the sliding window and we'll be going through image pyramid as well. So what have you done? You have taken a window, you will crop out that portion, and you will feed it to your classification object, which will be having a classification and regression of a bounding box as well. But after that, you will scale down your image. You will again scale down your image, and that's how it proceeds. First of all, let's say you have your original image, and you have this sliding window, and this will be sliding through whole image, and it will be detecting the smaller objects. In the first example, I don't think so it will be detecting anything, right? Then again, you reduce the size to a lower dimension. Again, the window size is same. It will be going through whole image. Now it might be able to take out some of the objects which are of the medium size. And again, you scale it down to the third time. and you might get a man over here. I guess you will get a man over here, but you might not get the bicycle, whole bicycle. And again, you will have to scale it down to further. So what is hindrance here? Now again, the hindrance comes is computation. What are you doing? You are making a sliding window that will crop the things again and again and send it to your network. Your network will be doing classification task. If it doesn't find out any object, the sliding window will slide. In the whole image, it won't find out anything. Then it will go for the reduction of your dimension. Again, the sliding window will perform sliding, cropping of the image, sending it to the classifier or net, whatever you have, and the classification task will be then. Again, you will not find anything, and this time this thing might go for 6 different variation of your resolution. Now imagine how much computational this thing will be. Feeding, how much images will you feed for a single image for detection? This doesn't sound anything good, right? This much computation for a single image to detect just 2 objects into it, sliding again and again, cropping it again and again, and then again the image pyramid kind of thing. So we have to find out some way out of it. Again, one more problem you can come up with is, let's say you have a sliding window over here. You have a sliding window over here. Okay, here. And it will be sliding over this thing. Okay, at the starting it will be sliding over this. But tell me, do we have any intelligence over here? Like, do we have any intelligence in the sliding window that where it should be sliding? Just look at this image. This portion doesn't have anything into it. Why should I crop this image? Why should I slide on this image, this portion of image, and send it to the classifier? This is useless, right? Waste of time, waste of computational power. Similarly, if you look here, this portion doesn't have any objects inside of it. So what is this? This is waste, right? Already you are seeing that how much computational it can go. You have to crop the image, right? You have to go through all the variation of the resolution of the images. You have to slide through the image. You don't want it. Can't we do something of it? We want to reduce this thing, this useless things. We don't want to go through this portion of images. And now here is where the need came, and something came into picture. Okay, before that, so these are our region of interest, right? We want to detect this thing. This is something which may be something which will be making sense to send to the CNN architecture to detect something out of it. It won't be making any sense to this thing. So I have so red color portion is not of any interest, and green color is something which is of our interest. So we want something which will tell us, like, use your sliding window on this portion only. Use your sliding window on this portion only. You will find something out of it. Don't use it on something like this. This doesn't have any information inside of it. Okay. So this is what I have written it again. Problem with sliding window technique. It was a brute force method. And again, you have very small images, and those were with the giant counts, right? Huge amount of images you have to take. You have to crop them, you have to slide, and again, you have to go through all the variation of resolution as well. And we don't want to do that. We want to have some smartness, and there are algorithms which came into picture, which smartly tell you that these are the reasons. Go for these regions. This will be helpful to tell you that there is something inside of it. There might be something inside of it. Don't go randomly through all the images, all the portion of the images. Don't go through all the images, all the portion of images. Go through the selected areas. Those might be having some interesting objects inside of it, and you can do the classification of it. Okay, so what is that? Which is that algorithm? So there are some algorithms. There are many algorithms actually, but we'll be seeing only 2 of them for here, and our major interest will be looking forward what that is. But for now, one of them is age boxes. Now, if you're not aware of, let me tell you, there is something known as counter maps. Okay, now counter maps gives you all the boundaries of your images. Don't look at here. There's nothing to see, but you might have studied somewhere. No, you might have seen what are counter maps. So it makes use of that thing. How does it make use of that thing? We have to see that. So let's take an example. Let's see this lady. Now, what are counter boxes? Counter, they draw the lines around your boundaries. Okay. So you can see this lady here. What the age age boxes will do is it will draw first of all contour map of a given image. So you can see these are the contour maps. This one, this one, this one, this one. These are just like boundaries of this provided images. Now it has detected that this area is having something inside of it, and you can send this area. In this image, it has detected this thing, a bicycle. In this image, it has detected a person. This might not make sense, and this might not have any sense out of it. Okay, it has. Okay, you can see there is a horse inside of this image, this portion. Here also you can see there is a cow inside this portion. But how did it find it? How, with the help of the contour, it came to know that this is the portion and we should be sending this portion to our CNN architecture and nothing else. At least we saved other computation, right? We didn't went for this all portion. We saved our computation. But how did it came to know? The magic is, there isn't something like magic, but let me tell you what happened here is. Okay, where is the eraser? Okay. So what it does is it finds out, first of all, it initiates a sliding window again. Okay, it will have a sliding window, and what the sliding window will do is it will find out the area where you have full contours inside of it. It will count the full contours divided by total contours out of that image. So if you see here, you have the full contour of a lady in this box, and divided by the full contours, you might say this is a full contour, this small box over here. There might be a small edges there which will be forming a contour, but this is the portion of an image which is having a contour. And when you calculate like total number of contour inside that box divided by total number of contour out of that box, it will result higher value. And that's how it detects like this is the portion of image that is of interest. Now the question comes, we were running off this sliding window, right? We don't want sliding window. Why didn't we want it sliding window? But because in last scenarios, we used to have a sliding window. After each slide, we used to send that to CNN. And CNN used to take a huge amount of time for classification of those images. Now, though we are using a sliding window, but imagine it, we are not sending all the images, right? We are not sending all the portion of images. Now we are sending some selected portion of images. So in this way, you don't have to use your CNN architecture again and again. Just using it once for the region of interest told by your age boxes algorithm, it bears you good output, right? And your computation will also be reduced, and your time required will also be reduced. So this is how age box algorithm works. So I wanted you guys to be aware of age boxes, like this kind of algorithm. This is how the people bring intelligence into their algorithms. Okay, so we'll repeat it again. Like, what was the formula? We will find out the total number of full contours inside of that image, inside of that sliding window, and outside of it. And whichever box will give us a bigger value, that will be our region of interest, and that is the only region we'll be sending to our classification algorithm, or let's say classification architecture. And that's how we saved our time. We are not going to CNN again and again for the portion of image which is not having anything inside of it. Okay, so next algorithm that is of our interest is selective search. Now selective search was something like selective search is something which will be helpful for our CNN family as well. So that's why I want you guys to know about selective search. What a selective search will be doing is it will be forming. Okay, just look at this image and just look at this outcome of a selective search. At the first iteration of a selective search, it draws some patches, right? Now these patches are drawn with keeping in mind with respect to color, texture, and might be the combination. Okay, what combination is, you will get to understand. But texture and color. So let's say if you look at the sky, okay, the sky is having same kind of color. So it is colored as something like light yellow. And if you look towards this this pole, it is colored something like yellow, right? After that, what happens, it is having intelligence inside of it that it can think of, if the textures are similar, it will combine those separate patches as well, and you will be reduced with this kind of patches. Like you will be having less number of patches in the next iteration. And you can see we have a same color for whole cow. So this cow, wherever that is in that image, you're getting a similar color for it. For another cow, you are getting a red color. For sky, you have some different color. There will be some misleading also, like this bars are there, right? Some wires are there and it is not able to detect that thing properly, and some different color it has done. But now you have reduced the interested regions, right? You have, how many regions do you have to send to the classification task? You will send this yellow, maybe a red, maybe, and blue, maybe, and this red color pole, maybe, and you will ask your model to predict on it. So if you're not getting it right now, we'll see in the further slides as well. Okay, one more thing I want you guys to know is SVM. We talked about it, right? Okay, that thing will be useful in RCN family as well when you proceed further. But before that, let's see about selective search. So when selective search was introduced, it was in 2012. So 2012 was the year when selective search came into picture, and this algorithm was able to segment out objects inside an image. Okay, now segmentation is not easy. It's something different. This is something hard. Okay, if you see this, if I ask you, there are multiple kittens inside this image, and if I ask you to differentiate between them, so what will you say? You might say that okay, so you might say that let's differentiate based on the colors. You might say that this is having different color than this might be having slightly different color than this, and you will be able to say that this is a different kitten and this is a different kitten. But imagine a second task. You have a chameleon, that too in forest, let's say on a tree, and now you see, can you differentiate between colors? Now through your eyes you can, but imagine it for an algorithm, imagine it for a computer to do that task. You can't do it, right? This is also green, this is also green. How will you differentiate them? So the next thing comes into the picture is texture. So based on texture, you can say that this object is different from the background. If you come here, it might not be the case, because all of them are having same kind of texture, right? These are differentiated based on color, and this image of chameleon is differentiated based on texture. So imagine what and all things might be inside the selective search algorithm, which is taking this intelligence into picture and differentiating and making the segments out of it. Okay, one more task, one more difficulty for it is, let's say you want to segment out a full figure of a man, but look at it, the face color and his body color, like he's wearing a sweater. So look at it, on the basis of color, you won't be saying that this belongs to the same object, like this face belongs to this body. If you say on the basis of texture, this is also not the case. The texture of sweater is different than the texture of his face. So imagine it, how difficult it might be. Now look at this image. Let's say you want to segment out a whole car from an image. Now look at this color of a car. This is white. Now look at the alloy wheels. Those are red. So on the basis of color, you can't say that this both things are together. If I say texture as well as texture is also not the same, right? This is a plain kind of surface. This isn't a plain kind of surface. So just imagine how intelligent the selective search algorithm must be to segment this thing together. So it takes into this kind of thing consideration, texture, color, and another thing which is known as combination. So it is able to find out that yes, this is a wheel which is closer to this kind of object, and it fits well inside this this curve. So it belongs to same object, and I should color this whole object as same with same color, and the wheels should also get the same color. Okay, so I guess I made you aware of what the importance and what the difficulties are, how complicated the selective search algorithm might be. Okay, let's take one more example. This was published in the paper itself. selective search. So you can see there is one lady, there is one television. So when it starts, when the selective search algorithm starts, it's randomly based on the color and the texture. It just randomly allocates them some segments or say colors. And in the next recursive steps, what it does is it combines different segments on the basis of texture as well as color as well as combination. What was the combination? Combination was like if two different objects are like they are fitting into each other, they will be a same object, and hence they should be colored as same. So look at this. Okay, just look at this, how intelligent it is. And the next step, it is again iterating it, and it is able to reduce the number of segments, and you can see the segments. And now you have the region of interest. You can just send this portion, maybe this color of portion, and you will be able to detect that there it is a television and here it is a lady. Okay, so I guess you got the feeling of what selective search algorithm works like. It generates some initial sub-segmentation based on color, texture, sizes, and shapes. Combine them based on their shape, similarity, textures, and size similarity. And finally, you have some regions with you, and you can send only those regions to your classifier so that you don't have to go again and again to your classifier architecture. And you can save your time as well as the computation. Now let's jump on RCNN's family. So RCNN is also known as, not also known as, it is known as region-based convolutional neural networks. And this is the person who was very much intelligent because he took all the things together and he built something known as RCNN. Okay, he proposed this thing into 2014. So we knew that this selective search was introduced in 2012. So he took use of that thing, feature extraction of the given region. So for that, he used to have this convolutional neural networks, because those, like in 2012, we have that AlexNet, right? So AlexNet became famous. So he took these things together and built something known as RCNN. And at the end, you have a classifier. Now, what the classifier is here, this classifier is SVM. So what we have seen in classical CNN, this classical CV2 approach, we have seen that they are using SVMs, and this guy also started using SVM there. So look at his architecture, what he did. So he had an image. After that, what he did is he found out, he ran a selective search on it. He found out the regions which were of interest. He passed only those regions to the convolutional neural network. And he used the same kind of arrangement what we have seen. We have a bounding box regressor as well as we have an SVM, which SVM will be giving you the confidence and the classification, and bounding box regressor will be telling you the boxes around those images or around your objects. So he was pretty much smart. He knew. AlexNet was introduced in 2012. You have your bounding box regressor before that. You have selective search in 2012. He took help of them and he just put this thing together and he got something which is far more powerful for object detection at that point. And that's why I want you guys to know about background of all these algorithms. You just don't know what kind of thing will be helpful for your kind of approach, for your kind of project. Okay, just for your knowledge, SVM was introduced in 1995. Just imagine the 1995 technology coming into use in 2015 or 2014 for this kind of thing. And this is the motivation, right? This is why you should know about this kind of algorithms beforehand, if in future you're gonna engineer your own. Okay, let's go through it once again fastly. So he has this proposals. How did he generate this proposal? He used that selective search kind of thing. Selective search kind of thing, use this texture and color. Based on that, it generates some segments, and only those segments he used to send to the network. So basically, he kept that something like 2000 he has mentioned in that paper. So he used to have those 2000 region of interest, and he used to feed it to the convolutional neural network. Outside of the convolutional neural network, you have two other things, which are SVM and you have bounding box regressor, using which we have the classification as well as the bounding box around your objects. And what is the disadvantage over here? Disadvantage is you have 2000 forward passes. Now imagine you have 2000 region of interest and you are passing it again to the CNN. If you don't use region proposal method, you might be going for sliding window. Now imagine how much sliding window might be giving. If the selective search himself is giving 2000 region of interest for performing good with the architecture. Imagine it. Now we don't want this thing. Don't want that our architecture should be invoked 2000 times for a single image. And also you have to train 3 different models here. You have to train your CNN architecture separately, which will be extracting out the feature. You have to train your SVM classifier separately. You have to train your linear box separately. And that's a time consuming task, right? And you want to remove this thing. And that's why there will be the emergence of fast and faster RCNN. So let's move further. So came the fast RCNN. Now the same person who invented RCNN came with fast RCNN in 2014. Just 1 year after, he came up with the thing which is known as fast RCNN. Now what the fast RCNN does is, instead of sending whole image, instead of doing the selective search on the image and then passing 2000 images to the CNN architecture to find out the features out of it, he used to first pass that image to convolutional neural networks. After that, he used to run a selective search on it. And after that, he used to do the region of interest pulling. Okay, so what the region of interest pulling can be? Okay, so you have an image, you pass it through your convolutional neural network, you have some more channels. Okay, you must be aware of channels if you're coming from CNN background. And now the features are not exactly looking just the way it used to look on the image. But then also you can run a selective search on it. You will get an object there and you can do ROI pulling. You will pull out that portion through whole of the channels. You can imagine over here, if this is the portion which is indicated by the selective search algorithm, you can extract out just those portion out of that stack of features, feature maps. And then you can pass it to your classifiers. I mean to say that bounding box regressor and your confidence score SVM. Okay, so this is how you saved your time. How did you save your time? You're not passing 2000 image again and again to your CNN architecture. You're passing it only one time. After that, you are running a selective search algorithm on it. And after that, you are doing region of interest pulling, and that you are passing it to your further network, SVM or say bounding box regressor. So you reduce that cost. What is another thing which it helped with? I guess nothing. Just one thing it helped out with is you don't have to send 2000 images at a time. Okay, then came, okay, how does it look? It looks like this. You have a convolutional neural network. First, you pass the whole image through convolutional neural network, and then you have the region of interest pulling over here. Before that, you have selective search here that will be telling you the region of interest. You can pull them out, and then you have something known as fully connected layers, which after that, which ends with the bounding box regressor, as well as something different is here. Earlier, we were using SVM classifier, but in this architecture, he was using softmax classifier. Okay, let's move further. So as you can see, we are not passing 2000 images separately for a single image through the convolutional neural network. So we are saving our time. Okay, I was confused with it, but yeah, there is one more issue that it solved. The issue is we had 3 different networks, right? We had the convolution network, we have the support vector machine, we had the bounding box regressor, and we have to train it separately. But in this kind of architecture, what they have proposed, you don't have to do it separately. You can train it parallelly. All those things can be trained parallelly. All this 3 different classifiers can be done parallelly, and you will save a time there also. Okay, now came your faster RCNN. Okay, in faster RCNN, what they did is, similarly, they will be passing whole image through a convolutional neural network, and you will be getting feature maps. And now, one thing that was bottleneck in RCNN and fast RCNN was they were using selective search. Now, selective search is also computationally too costly, and we don't want that thing. So what they did is, they think of it as like, just imagine we have some boxes. Now, you know what kind of classification you are gonna do with your object detection thing. It might be a man, it might be a car, it might be a cow. So this box might be good for cow fit. This box might be good for your human fit. This might be good for a dog, let's say. So what they were using, they were doing is, they used to take the convolution feature map, which was the output of your convolution operation, and they used to run this kind of windows out of it. And whatever, if there is anything, they used to feed it to your classifier. Okay, this is how they saved their time again. We have to run fast because we are losing our time. We have some more things to see. Okay, so what do we see? We have seen fast RCNN, we have seen faster RCNN, we have seen the simple RCNN as well, and the whole thing was to reduce the computation. Okay, next thing which was introduced was masked RCNN. And in masked RCNN, can you do the classification or detection pixel wise? This was the task which we want to have. And to your no surprise, it was again Girshik who was also in this task in Facebook AI, and he did this task, and they had this architecture which was able to classify or detect a pixel wise. You can see there is a man, and pixel wise we can color them, and then we can detect them as well. There are cars, those are separated pixel wise, as well as you can have bounding box across it. And so Girshik was everywhere. He was into masked RCNN. He was into he was into RCNN, fast RCNN, faster RCNN as well. So remember that name, remember that personality. He's he is well known for object detection kind of algorithm industry. So now let's see how much faster this kind of algorithms are. So if you look to RCNN, these are like, it takes 50 seconds to process only one image. Just imagine how much computational it was to have a RCNN. Even though we had selective search, right? We were not using sliding window. Imagine using sliding window, you might be taking 5 to 10 minutes again. We had the intelligent tool that was selective search, and using that even we required 50 seconds to use RCNN for object detection. When it came to fast RCNN, it reduced down to 25x. It's like 2 seconds for an image. And when you go to faster RCNN, it reduced down to like 250x and 0.2 seconds per image. Now, why it is important to see how much time it takes? Say if you have a real-time application, you will definitely worry about it, right? Okay, it's going kind of boring, I guess, for you guys. Okay, let's have one question. Tell me what is like frames per second for your cell phones. Write in the comment section. Let me know how many frames per second your cell phone captures using whenever you start video recording. Come on, guys. Write in chat section. Let me know. 24, 24, 30, 30, 60, 90, 120, 20 and 30. Now imagine if this kind of algorithm is inside your cell phone, which takes like 0.2 seconds for processing just one image. Now, now we have this much advancements. We have like 30 frames per second, right? For 1080. Can you use this thing? 30 frames per second your cell phone is capturing, and this guy is taking 0.2 seconds to process that and to tell you that there is an object inside of it. Come on, you don't want it. This is too much slow, right? So we started with sliding window. We came to RCNN. I'm sorry for that. We are running late of time. That's why I take some fast jumps, but you guys can read about it. Sliding window we have seen. Then sliding window has some disadvantage. It was taking too many regions of an image into consideration, and we don't want that. We jumped to selective search algorithm, which was used in RCNNs. And even though it was using selective search, it was taking 50 seconds per image. And then we had the advancement in fast and faster RCNNs that you have seen, and those reduced the computation. And that's how we got to 2 seconds and 0.2 seconds for fast and faster RCNN respectively. So whole study lies behind reducing the computational time. And that's why in 2015 came an architecture which is known as YOLO, and it got famous. So if you are someone who want to work into CV2, who want to work into computer vision industry, who want to work into this object detection algorithm, you can't skip YOLO algorithm. You will have to deal this thing. This is something your faster RCN can't even achieve closer to it. Why I see like that is, okay, this is a map of it. Okay, will there be any practical demo today? I guess we'll not be having, we have too much slides left today. That's why practically we can't have it today. Okay, let's focus on current slides. Okay, just look at this outcomes. You have a RCNN, this is not a comma, this is a point, 0.02. So it used to process 0.02 frames per second, and the value increased as the advancement increased. You came to faster RCNN, 7 things per seconds. Then okay, you have some variation inside of it. You have seen, right? Faster RCNN used a convolution neural network inside of it. You can change it. You can have AlexNet, you can have VGG16. Accordingly, your time will change. But something like this 7 is achievable. So you can have 7 frames per second. Now you don't want this, right? You have seen your cell phones, right? 30 frames per second. How will this thing work there? Okay, so then came YOLO V1. Now YOLO V1 gave you 45 frames per second. And now came the second version as well. It gave you 91 frames per second. Now look at this graph, dude. Right? It's amazing how this thing has improved. But if you see, there is something known as accuracy. If you are not getting, if you're not aware of how this accuracy are measured, we are going to see this thing at the end of the slides. But for now, just look at it. The accuracy went on decreasing, right? It was somewhere 73.2 for faster, and it reduced to 63.4, right? And this is a trade-off. This is what we are worried about in current computer vision field. People are developing algorithms which are able to process with higher frames per second, but the accuracy is less. When the accuracy is more, the frames per second is less. And this is where the trade-off is. So you can manage with any algorithm which can give you a good amount of frames per second. Now you have seen in your cell phone itself 30 frames per second. So you can use YOLO algorithms. You can see they have any count about 30 only, right? 45, 91, 81, 67, 59, 40. So these are good frames per second which you can use. Okay, so this is one of the big, I can say, status of an algorithm which you will decide on for your application. If it is a real-time application, you will have to go for YOLO algorithms. There is some other algorithms also, RetinaNet and all. You can go and check out their frames per second as well. But for now, just focus on YOLO. You can go for YOLO. Okay. And talking about faster and fast RCNNs, they have a huge accuracy. So if you have some task which doesn't require a real-time identification or detection, you can go for these algorithms. They will do detection, though they will be slow, but their accuracy will be more. Okay, let's go for YOLO algorithm. So guys, I have taken the slides from Code Basic YouTube channel. So you might be knowing about this person. If you know about, just comment down in the comment section. I want to know who all you know about this person. He's a famous YouTuber for data science YouTube channel. Let me see who all know about him. Can you name him? Come on, we want to be interactive. Okay, you might not be able to recall his name, but he's very famous. I took some snaps from his channel, his own PPT. So you can go through his channel as well, and you can study there. For now, let me take you quickly through the YOLO algorithm, how it works. So how will you train your YOLO algorithm? How it is trained? So let's say you have a dog here, and what will be your training vector? So we have seen at the end, you have a softmax layer. There you have a log function for training, and okay, channel name, his channel name is Code Basics. Okay. So I will drop the links as well for this channels, whatever I have preferred. Now I'm also studying. I'm also through my learning phase. So yeah, I will drop the okay link as well. Okay, let's concentrate here. let's say, how will you create your vectors for training your this YOLO architecture? How is it trained? So it is something like you have something first, which first attribute which tells you whether there is this object inside your image or not. So yeah, there is an object. So PC will be one. You have BX, BY, BW, BH, BW, and BH. So what are this? These are coordinates, guys. So BX and BYs are the central coordinates. You can see a yellow dot here, and you can have those coordinates here, BX and BY. After that, you have to tell the width and height. Okay, width and height that you have here, and you have to tell which class it belongs to. Already we have told that there is some object inside of it, but which class it will belong to? It can be a dog, it can be a person. So for in this scenario, it's a dog. So in front of C1, which is the class of a dog, we have 1. Similarly, if you have a person here, you can have this PC as 1. Yeah, there is some object inside my image. Then you have the bounding boxes coordinates. Then we have to tell which kind of class does it belong to. It belongs to C2, right? C2 is a person class. Let's say if there is nothing in the image, how will you create your vector? It will be like 0, that there is nothing in the image, and all other things are not of any interest for us. It can be anything. So this is how your vectors will be your vectors you have to generate, and you have to train your YOLO algorithm on. And basically what it will do is, next time, so this is how you will train it, and next time whenever you will feed an image into it, it will tell you whether there is an object inside that image, what are the coordinates of that object inside that image, and which class is it. Is it a human or is it a dog? And if the PC is 0, you can interpret that there is nothing in the image. I hope you guys got this thing. It is very simple. Next thing is, okay, you can see this example. You have a dog and you have a convolutional neural network which was trained accordingly, and then it outputs you 1. That means there is something in the image. It tells you what are the coordinates for bounding boxes, and it tells you which kind of object is it. Is it a dog? Yeah, it is a dog. And then you can have a bounding box across it. So it's not like it will draw the bounding box across it. Okay, someone is saying chain is also a element. Let's mute your microphones. Who is it? Okay, leave it. Okay, so what do we have? We have an architecture feeding an image. It will tell us what are the coordinates, and it will tell us whether there is an object and which object is it. So isn't it far better than the previous architectures? We have in the previous architecture, we used to have an SVM classifier for classifying which object is it, right? We used to have a bounding box regressor to tell us which where is the bounding box, right? And then we have a CNN to extract out the features itself. But now in this architecture, there is one single architecture which is doing all the tasks together. So you don't have to change this. You don't have to go through all the other things like bounding box regressor, then your SVM classifier, then you have the starting with the CNN, which will extract out the features. So this is good, right? One time you can do. So this is what it is said as. And one more thing is, in case of CNNs and all, you used to have that region proposals, right? And you will pass that region proposal again and again to your CNN, your classifiers, and they will classify it. But in this case, you don't have to pass different portion of your images. You just have to pass a single image, and looking at the single image, it will tell you whether there are multiple objects, whether there is a single object itself, right? So that's why it's named as you only look once. Your architecture will look the image only once. You do not have to see the portion of your images, just like the way our CNNs does. And that's why it is computationally like time. It doesn't consume that much time what the RCNN family consumes. Okay, so let's say there are how do you label these things, right? How do you have this vectors? So what you have to do is you have to divide your whole image into grids. Now these grids, whatever given here are 4x4. You can have multiple grids here. Okay, you can have 16x16 as well. It's your choice, 9x9 as well. And for each grid, you have to create this kind of vector. Now in this image, we don't have anything, right? Not of our interest. So it will be 0. PC is equal to 0. Similarly, for all other boxes, it will be 0. Even for this box as well. We want to find out the box which will be having the center of our object. For this box as well, this will be the same thing. But for this box, in this box, we have a center of our dog. So what will the vector corresponding to this dog look like is, you have 1 here, which is telling you that, yeah, there is some probability of having an object. And which object is it? It is a dog. Then what are the coordinates? These are the coordinates. It will tell what are the middle coordinates. It is 0.05. It is 0.3. What is the width and what is the height? That also it tells. And each of the bounding box, each of the grid box will be having the coordinate system like 0 cross 0 and 1 cross 1, 0 comma 0 and 1 comma 1. Similarly, for this woman, we'll be having something like 1 in this bounding in this grid cell. Okay, not in other grid cells, because the center of this woman is in this grid cell. Then you go to it, you get 1 in PC. That means there is some object. You get the coordinates for your center point, and around the center point you can have your width and height, and that's how you get your bounding box. And you can label it by this other attributes like PC, which class it belongs to. For this, the second C2 is 1. That means it's a human. Okay, so this is what it is. And for this each grid cell, you will be having how much? 1, 2, 3, 4, 5, 6, 7. 7 things for one grid cell. So it will be looking something like this. So you will be having 4 cross 4 as dimension, and you will be having, just imagine it is having 7 channels inside of it. Okay, for each grid, it will look something like this. So you have to train it on this kind of data. Okay, so now comes this thing. Similarly, for this image, you will fit and you will train it on this kind of vectors. And for this image also, so you can see for all the images, you have to create this kind of stacks, and you have to train your convolution neural network. And if you want to study more about it, what kind of architecture is used inside it, so note down darknet. Darknet is the architecture that YOLO algorithm use. They have their own website as well. I will leave the link for it. It's very much interesting. Go through it, what type of architecture they use. And yeah, let's proceed further. Okay, so this is how it will work. You will provide an input image to it. According to the grid cells, it will tell you where the image is, where the target object is. You can draw a bounding box across it. Okay, now the thing is, what happens is your algorithm will not give you that much accuracy. It might predict multiple bounding boxes around your image. So in this image, you can see a woman is having multiple bounding box around it with confidences like 0.9, 0.7, 0.65. And for dog as well, it has predicted 2 different bounding boxes. Now the thing is, you don't want this thing, right? You want only 1 bounding box. Why to have multiple bounding box? This doesn't look good. What can you do? Let's take the first situation. You might think, let's take the highest confidence bound, the box which is having the highest confidence throughout the image. In that scenario, you will be losing out your dog, because dog is having the confidence of at max 0.8 and the human is having the confidence of at max 0.9. So you don't want that, right? What will you do? So let's say the second scenario, you will segregate out the bounding boxes of humans separately and animals separately. And you will say that in humans, I will find out the bounding box which is having higher confidence. So let's say this one, you can say in this example, this bounding boxes, there are multiple bounding boxes. You will say, I will keep the 0.9 itself. But that will also not work. Let's say there are multiple humans inside that image. What will you do? Multiple, if you classify all the bounding boxes as humans and cats or dogs, and in human class, you will take only the maximum confidence bounding box. You will be missing out the bounding box for the human which was having less confidence, but though it was a human, right? You don't want that thing happen. So in that scenario, something known as IOU will come into picture, intersection or union. What you will do is, you will find out the bounding boxes which are having higher IOU. So what is higher IOU? So what you will do is, you will find out the area of intersection of 2 bounding boxes. Let's consider this wide bounding box, and you will go through all the boxes in your list, what your algorithm has predicted, and check out for this metric. For that, you will find out the intersection of those both bounding boxes and divided by the union of both bounding boxes. So this intersection of over union will be more. In case it is more, that means they are pretty much the same kind of thing. And what you can do is you can just remove one with lower confidence. You can see if you see this bounding box of a dog, and if you see the bounding box of, let's say, human, they are having pretty much less area of intersection, and that's why their intersection over union, this formula will bear out less value. And you can set that threshold yourself as well. Like if it crosses this much threshold, that means these are providing to the same class, same object, and you can remove them. So for this, it is lower, right? If you consider it 65%, it is lower than 65% for this intersection. So you will not remove this box. You will just get the set of these boxes which are having the intersection of closely 65%, and you will take only the bounding box which is having higher confidence. In this scenario as well, if you have another human in the image, you will not be having that. Let's say that human might be here, so you will not be having that bounding box intersection more with this bounding box intersection, right? And that's why you will not be removing that bounding box. You will be just taking consideration of this bounding box in case you are predicting for this object, and will be removing that. So that is the importance of intersection or union, to find out which is the bounding box you should keep out of all the bounding box that your algorithm has told you. Okay, and that was known as non-max separation. Okay, you didn't went for only max separation. You didn't do like, let's take the maximum confidence bounding box. You look at the IOU. You look at which bounding box are having higher intersection, whichever was having a higher intersection, and among them, if whichever was having the higher confidence, you just took that bounding box. And this is how you got clear with it. 0.9 for human and 0.8 for dog. We didn't miss the dog here, right? Now there might be a situation where you might have multiple objects inside the same same grid. What you can do is you can have the concept of anchor box in that scenario. Earlier you used to have this count as 1, 2, 3, 4, 5, 6, 7, right? Now you can do is you can extend this vector to 14. What you can do is half of the portion for dog, half of the portion for the person. You can see the first anchor box. You can see there is an image, there is some object. You can have a bounding box coordinates, and inside that, for whom it is for a dog. For second portion, you can see there is an object. You have a bounding box. For whom it is for a person. You can attach them together. You can create a big one. So in this case, you can have multiple detection of multiple objects inside a same grid. And yeah, you will have to create this kind of anchor box, this kind of whole vector for each and every grid. If they are not there, just keep it 0. Just keep it PC is equal to 0. But if in a grid, if both the objects are coming together, then you have to create this kind of anchor box. Both the anchor boxes coming together to create a bigger one. And then if you have such kind of image, you can pass it and it will give you 16 kind of this thing, right? Okay, let's just move and let's just see what is the power of YOLO. Okay, on Coco dataset, you can see YOLO v3 version 3. You can see the frames per second, right? Look at it. So MAP is there. Map, we're gonna study it quickly, but first of all, look at FPS. Look at the FPS they are touching. They are touching 45, and some one more algorithm is there, that is YOLO v3 tiny. So there are versions to it. Okay, it's not like YOLO version 3 is individual. There are versions to it. So look at the frame rate they are achieving. I don't think so anyone else is close to enough, right? Your YOLO version 3 tiny is achieving nearly 220 frames per second. So this is a website for it. I have given you the link for it. You can go through these websites. This is the official website for this darknet/YOLO. Go there, and if you want to try out this experimentally, you have the link for the weights as well. You can download and you can configure and you can run these algorithms yourself. And if you want to read some good Google Colab notebook on that, so that also I have given the link for. There they have shown you how to use YOLO version 5 yourself. Let's move. So yeah, YOLO didn't stop there, guys. YOLO came up with recently with the version 5, and just look at the frames per second they are touching. 455 frames per second. On what is this, right? 345 frames per second, right? You have versions into it, small, medium, large, whatever you can say, and you have some meanings for this as well. Average precision, we will look at to it. We will look to it, but I want you guys to get a feel of it. What we started with used to take like 50 seconds with RCNN. Now where are we? We are like 45 frames per second. And in YOLO family version 3 were giving us nearly like 45, 35, 20. Now it's like a huge jump. Then like after YOLO version 3, there came YOLO 4 as well. Then came YOLO 5 as well. And the thing they are behind is increasing the frame rate as well as reducing the error rate and increasing this mean precision average, this thing MAP, this AP. We'll get to know in further slides. We'll quickly go through them as well. And look at the parameter count they are taking. So you can see 87 million parameters for this YOLO version 5. But yeah, which is giving us good accuracy. And frames per second is 40. I guess this is good with us, right? We have 30 frames per second, what we have seen in our cell phones. Yeah, but there might be some applications there we have multiple, like the frames per second might be more. So there, this kind of algorithms like YOLO version v5, these are like top-notch architectures. It can be useful. Go and study about this thing, guys. I've given you the link about it, Google Colab link. You can study how to implement YOLO version 5 yourself. Okay, so brief study about it. When does the YOLO version 1 came? It came 2016. And Joseph Rendman, you should know about this man. So we read about Girshekro. So he was the one who gave us RCNN family. Now look at this person. He is into YOLO algorithm as well. So this person was into mass RCNN as well. This person is into YOLO algorithm as well. So he has a huge contribution, guys. And this is the Joseph Redman. So he's also a big personality in this object detection area. Do read about him. He's a very talented person. If you go to his TEDx talks, you will get to know what kind of thing you imagine for us for object detection technologies to go. He has 2 tech talks on it. So go for it, search for it at Joseph Redmond talk on object detection. So 2016, we got our first YOLO. 2017, we got our second YOLO, which was giving us a tagline, better, faster, stronger. Again, who was inside of it? It was Joseph Redmond and Ali Farhadi. But what happened in YOLO v3 was Joseph Redmond stopped working for it. Actually, if you go through his TEDx talk, he's worried about misuse of his detection technologies in army, in wars. And he was very much affected with it. And he thought like he should not keep going with this work, and he stopped using it, studying it or improving it. So on TEDx talk, you should go and you should see. He will he tells how army and countries are making this misuse of his algorithm for mass destruction, and that's why he took his legs back and he stopped working on YOLO versions. But after that, this person Alexei, he forged his directory and he kept his work continuing. And we got YOLO version 4 in 2020. So this is a recent, okay? It's very much recent. YOLO version 4 also came into market like 2020, 1 year back. Okay, and in now 2021, you have YOLO version 5 as well. And not just YOLO version 5, you have various versions to it. Okay, now we'll go through how to find out that mean average precision. We have to go through that quickly. So let's say you have this image and yellow colors are the down truths, and you have something, let's say you have an object detection algorithm which detects like the red box is the detection. Now, do you say that this thing, this detection is good? Yeah, it is able to detect out a human, but it is not good, right? Imagine this thing being used for your autonomous cars. It will be mass destruction. And if you go for something like this green box, it is also not that good. If you go for this blue box, it is detecting a person, but it is not fully detecting the person. So how will you decide which bounding box given or predicted by your algorithm is good? So that also comes in with this only intersection or union concept. So you will decide a threshold on it. Whatever bounding box it gives, let's say this is the bounding box given by the algorithm, the red one, and this yellow one is our ground truth. You will decide IOU threshold on it. So you will calculate intersection of these two bounding boxes and also union, and you will divide and you will take that fraction and you will decide on the threshold. If it is greater than that threshold, you will say that it is correct. So you can see this one, this will have an intersection over union lesser. This will be having intersection over union lesser than the first one, and this will be having more, right? So yeah, so if you see the green one and the red one here, that means it is a good match. The prediction is good. Green one is our ground truth and red one is the what the algorithm has predicted. And since the IOU score is more for it, it is good. We can say that this is a true positive. Now, if you guys are aware of precision and recall concept, in here, your precision will be true positive upon region of interest proposals. So let's say you have this red boxes as your proposal boxes. So what you can have is all the true positives. Okay, whatever the algorithm has given and which follows the intersection or union threshold, those boxes will be coming under true positives, and region of interest proposals will be having all the proposals, this all red bounding boxes. You can divide them and you can get the value for precision. For recall, you can have the true positives, like whichever bounding boxes the algorithm has given and are correct as true positive, divided by all the ground truths we have in that image. So here we have true ground truths, right? I guess I'm getting too fast on it, but yeah, manage with it for now. So yeah, this is how you get the precision and recall. Let's take an example because we want to see how the map term is calculated. So let's say we have 7 images. So in one image, you can see these green boxes are ground truths and red boxes are what the prediction, what the algorithm has predicted. And beside that, you have been given the confidences as well. So how do you proceed for it? How do you calculate map score for it? So what do you do is, first of all, you can see here we have the image indexes, image 1, image 1, image 2, image 2, image 3, image 4. And inside that, you go for the first detection. You can see that for the A, something which is detected, which we have labeled as A, it has a confidence of 88%. But you can see that it will not follow the IOU criteria, right? If you calculate the IOU for this thing, it will be too much less. At least if you have the option to select it, you might be keeping it 75%. But here you can see the IOU score will be too less, and that's why it will be something which will say at false positive. Algorithm says that this is your detection, but it is false, and that's why it is termed as false positive. Similarly, all this image will be having these things, will be having the confidences as well as will label that whether it is a true positive or whether it is a false positive. So something like this B thing, in the first image, you can see the ground truth and the prediction, they are overlapping with each other and they are having a high IOU score. And that's why we'll say that it is a true positive, and that's what we are labeled as true positive. So you have to create this thing. After that, what you can do is take the same thing and arrange it in decreasing order. Okay. So you can see 95%, which was at the bottom, it came at upper side. Okay, it came at upper side, and here, and one which was having a lower confidence like 14%, it came at the downward side. And then what you have to create a new column that is known as true positive, false positive. So what is true positive? Wherever this image is actually that bounding box was having the label as true positive, just have a 1 in front of it. And if not true positive, if it is a false positive, have a 1 there. Then you have to find out accumulation of true positives. So what you have to do is you just have to add. Okay, we have just a few slides left today now. Just 5 to 6 slides we have. Just bear with me. Okay, so what we have the confidences arranged in decreasing order. Then we have true positive and false positive notation. Then we have accumulation of true positive. What you can do is just add this thing, right? Whenever you move from up to down, how many true positives do you have? So for first example, you have a first true positive, just 1. In next example, you have just one false positive. So you have the accumulation of false positive as 1. When you move downwards, you will get again a true positive, so it becomes 2. Then you have to find out the precision and recall. So how will you find out precision and recall? Precision is true positive upon true positive plus false positive. So you should be able to you should be fine with calculation of that, right? You have true positive for that row, you have the false positive for that row. Just do the calculation, true positive on true positive plus false positive, you can get the precision. For recall, what you can do is true positive upon number of ground truth. So how many number of ground truth we had? We had something like 15 ground truth here if you count. So you can do that thing as well here, and you got the precision and recall columns. After that, what you have to do is you just have to plot them, precision across recall. You plot them together. Now the thing comes is, how will you find out map score out of it? So where did we start? We started from here, then we came decreasing order, then we had the columns known as precision, recall, and precision and recall. Then what we have, then we had a graph, right? Now we have to now we have to find out the map score out of this graph. How will you find out the map score out of this graph? There is some method known as 11-point interpolation. What you have to do is you just have to take recall on the x-axis and precision on the y-axis. What you can do is just plot this points on this graph. Somewhere you might have the repetition, like 0.133 is coming again and again. Yeah, I know we are going far beyond the time. Yeah, just bear just 2 minutes for it. So yeah, so you can see, yeah, 11-point interpolation method is used for finding out this graph, and you can have area under it. You can see the values of it. So what you can do is just 1 by 11 and all the values for this x-axis coordinates, like 0, 0.1, 0.2, 0.3, 0.4. Add them together, divided by 11, you will get a score which is known as average precision. And now we don't use this 11-point interpolation. We have all the new computations which are there, like Coco dataset and Pascal. They use all-point interpolation. What do? We just find out the area of them, and that gives us average precision. This comes closer to it only, 26.84 and 24.56. Next thing is, this is how it is used for measuring the accuracy. Let's see. This is a fast RCNN, and it was trained on Pascal dataset of 2007, and the mean average precision it got was 66.9. And again, you got this fast RCN which was trained on the data of 2007 as well as 2012, and you got the mean average precision as 70. And similarly, when you move forward, you have faster RCN as well. So you have the choice whether to train on a single data set, or you can train on the combination of data sets as well. And after that, you can have the mean precision accuracy. You can find them. And yeah, so what we have seen frames per second. We have seen mean average precision accuracy. Okay, so this is what is important. You should know algorithm should be having more frames per second processing, as well as higher MAP. So you find out average precision for all these categories, and you take a mean of it, and that becomes mean average precision. For the checking purpose, for Coco dataset, it is something different. What they do is they take out mean average precision for IOU threshold of 50, 55, and 95, like a difference of 5%, and they take an average of it, and that becomes the average precision for it. For every algorithm, you can see here, for faster RCNN, which has the ResNet as its backbone, you can see the average precision. This is AP50. I want you guys to know this thing, because whenever you're gonna read this kind of papers, you will be confused with what is AP50. So 50 means the threshold what they are allowing for IOU. So more lenient you go for the threshold, the higher will be your accuracy coming out. So here you have given the 50 as your IOU, and your accuracy is improving, but that is not good. If you become stricter on your model, like 75% as your intersection or union, it will reduce down your accuracy. And this is how you can see the average precision on small, medium, and large scale objects as well. Okay, now we are done with our slides. I guess you guys enjoyed. It took some more time to complete the slides, but I guess I gave you some of the information. If you guys have any doubt, or if you guys have any concern, you can type in chat section. Then we'll wrap it up. Any guys doubt? Any doubt, guys? I am also tired going through all these slides. Come on. So this is the importance of it. This map, what I've shown you. All these things come together and then they build something bigger. Okay, chat section. Okay. Can you share this PPT? Yeah, PPT will be shared, guys. Don't worry. Okay, on LinkedIn profile, you can search for me, Ankush Deshmukh. Yeah, definitely you can get this thing for reference. Now, education is free, guys. We are distributing these all things for free. We are not charging you guys anything. If we are charging you for your time, if you can bear it. Now, I saw someone telling me like we are going past 10, but as this is how much behind the object detection is. Anything else, guide from your side? Anything you want to say? Anything before we wrap it up?
Hello everyone. My name is Praveen Kumar, founder of towards machine learning.org. So as Ankush is asking for any doubt that you guys have, please feel free to ask him with regards to the session or any topic that you have not understood yet. Okay, we have the feedback coming in from Sapna already. Informative session. Big thank you. Yes, Jagdish, there will be sessions in future as well on explanation of algorithms in detail. Yes,
This
Nitish. Yeah, Ankush, go ahead, please.
This was too much for someone who is a beginner, but at least you will be having the slides with you. At least you will be having these lectures with you. Whenever you want to start your study, whenever you start your experimentation, you can go through the slides. You can go through the recorded sessions, and you will get much idea from it.
Okay. So thank you so much, Ankush, for such an amazing and informative session on the object detection algorithms. Computer vision application market is growing in the data science, and I hope this session must have helped every participant here. We generally supplement theory with the implementation using Python. That's what we have been following so far. But today's topic was so big and so vast, you know, that we could not cover the implementation part. So what we can do is we can cover the implementation part using Python in upcoming live sessions. So do not worry about it. We'll be covering the implementation part as well. And I guess that was one concern from someone in the session, I believe. I guess it was Sapna herself. And does that help Sapna covering the implementation part in the next live session? Okay. Thank you so much, Sapna. So as you all know, like for any event, feedback becomes very important to understand what one is doing right and where one can improve. So whether this initiative is helping the end data science practitioners or not, that we would get to know by the feedback only. So I'll open up this forum to have a quick feedback from all our participants. What do you guys think? Like this session was helpful? Did we deliver the knowledge that you were looking for? Any comment, thought on the content of the session? We had a couple of feedback coming in already. Okay. And by the way, guys, we have posted a poll regarding timings of the live session. So we want to get one common time that works out best for all. Right now it is 8 to 10 p.m. in the night. So if you guys have any other comfortable time, so do cast your vote. It will help us ensuring that everybody is able to attend the live session. Poll will expire in the next 2 days. So I'll request you guys to cast your vote for the live training session time. I'll paste the link here. So this is the poll link. Do open it up, cast your vote, whatever timing is comfortable for you. If you see there is some time that is not listed out in the options, do mention that time in the comment section. So we'll go to the comment section as well, and we'll come out with a common time that works out best for all. Okay. And You guys can open up the link and let me know in the chat window if you are able to open up the link. What do you see in the poll options? So I'll be sure that okay, you are accessing the right post. Meanwhile, I saw one professor joining the session. I believe it was Mr. Jagdish Kumar. So could you please unmute yourself, sir, and could you please talk few words about the session? Like, what's your overall feedback on the session, on the content, or the knowledge that's been shared in the session?
Yes, sir. It was very nice. We are very much thankful to the entire team. But however, the session is little bit advanced. Actually, the students might not having the basics part, which has been not covered in the curriculum also.
Okay.
So if it has been started with some basics, it will be better.
Yeah, definitely.
So could you please suggest some links where the students can go through so that they can understand?
Sure.
In the past, you might have conducted such sessions. You can share such links also. We can go through that.
Sure. Feedback taken, sir. Thank you so much for such a valuable feedback. So today's topic was talking about the evolution of the object detection algorithms, and we totally understand that we did not talk very specific or in very from very scratch the basics that you were looking for, maybe your college students were looking for. But we'll be having the upcoming live sessions where we'll be targeting one particular algorithm itself, let's say mask RCNN or the faster RCNN only, where we'll be talking in and out of the faster RCNN and the other algorithms separately. So we'll not mix up all the algorithms in one. So feedback taken. Anything else, sir, that you would like to talk about or would like to highlight?
Nothing particular, sir. Better you can unmute any one of the students. You can give the option to students, sir.
Sure.
They can share their views.
Sure.
Mr. Nitish Reddy is there, or any other students also. Yeah.
Sure. So I'll request all the participants, whoever is comfortable unmuting themselves, please unmute yourself and let's hear out from you guys. What do you guys think? Was this session helpful? Did we deliver the knowledge that you were looking for? Where we could improve? Are there any gaps? Can anyone unmute himself or herself?
Yeah, hello everyone.
Yeah, could you please give a quick introduction about yourself so we
Yeah,
all know who
myself.
we are talking to?
Yeah, myself Nitish Reddy, and I'm into like artificial in the learning phase. And right now I'm learning these things from past 1 year, right from the basics. And recently I have entered into the computer vision concepts. Like I already known these concepts like RCN and everything. Like I have known they work. But the thing what I have learned new here is like their evolution. Like starting from 1988, how they have evolved and everything. This was a great session. And as Jagdish sir mentioned, like it may be like who don't have a basic knowledge of CV, they might be confusing for them. But who is that like have a just like introduction to CV, they might. This is a wonderful session, and then I'd like to thank for Ankush for simplifying the things. He has gone through like in a very simple manner instead of going for the maths and how exactly they're going. He has given the idea and insights for in the future we can learn the things in depth if anyone wanted. And thank you for the team anyways.
Thank you so much. What name did you say? Nitish, right?
Nitish, yeah.
Nitish. Thank you so much, Nitish, for such kind words. And I would like to add in what you said. You talked about OpenCV, CV2. By the way, we had covered this topic in our past live session where we talked a lot about the OpenCV. We have talked a lot about the CNN as well. So what we can do is we can share you guys the link of a past training sessions that may help connecting the dots for you guys.
Yeah, that would be helpful. Yeah, that would be helpful.
Okay. Feedback taken. Thank you so much, Nitish. Anybody else would like to unmute himself or herself? Would like to talk about live session? A few words, maybe. What has gone good, and what went good and what went wrong? Anything that we could improve on? Anything that you are looking for in particular for the upcoming live sessions, maybe?
most of people I see here might be beginner, and don't worry if you guys don't if you guys don't get all of the concepts. Even if you get the idea of it, where to start from, it's good for you. At least you will be having all this content, and wherever you are, you might be in your final year, you might be searching for a project, something out of the slides will be helpful for you. So don't worry if you don't get the last session. I know I was too much fast on it, but whatever you have seen at the starting also as well, that will clear much vision for computer this field, object detection.
Yeah, as Ankush rightly pointed that out. And moreover, we'll be sharing all the content on all social media handles. We are on the Instagram, Facebook, we are on the LinkedIn. We have the website as well. We'll be uploading all the content on the website as well. Once we have enough responses from you guys, okay, whether you want that content to be out. So if you find it a bit advanced, or then whatever content we'll be sharing, all the links that we'll be sharing, you can go through them and have a better understanding of the topic. Okay, so the topic that's been presented to you guys is being presented after a thorough research on the topic. So team works really hard to present a topic for you. So Ankush has been working on this topic from a very long time. He has been researching a lot about the object detection algorithms, and today he is delivering that topic. So there's a lot of hard work that goes in, there's a lot of research that goes in. So we'll try our level best to make sure that we fill all the gaps and we deliver the knowledge that you are looking for. We have a comment from Vishal saying that so it will be fine if we conduct the 2 to 3 days like mini workshop with clear from basics and practical demo also, instead of one day like this. Feedback taken, Vishal, we'll look into it. Right now, idea is to pick up one topic from the machine learning or deep learning or computer vision applications and talk about it, talk from 0 to on the scale of 0 to 100% till 100%, I will say. Okay, and so that would incorporate the audience from the newbies as well and the people who are a bit advanced into the topic as well. But we'll look into it. Maybe we could divide the whole session into 2-3 days, so people do not have to overcommit for like 2 hours or 3 hours in one day itself. I've been seeing, like, I've been getting this message a lot, like how many slides are left. We totally understand, like, a topic was supposed to be wrapped up within 2 hours, that is 8 to 10 p.m. But we do not want to compromise the content as well, right? Because if we cut short the content to just 2 hours or 1.5 hours, then we'll end up compromising the quality, which we do not want. But we'll look into it, Vishal, do not worry. Okay, and we have been getting attendance link and the feedback link request. I'll do one thing. I'll you already given your feedback. I'll just circulate the attendance form right now, so you guys can fill up that attendance form, and so you guys can get the participation certificate that will help you a lot building your CV. I'm pasting a LinkedIn page, Instagram, and the Facebook page link as well. So make sure that you keep check on all of these to get the notification about our next live sessions. We put daily content on Instagram and Facebook, which will help you keeping abreast of the topics in stats, ML, NLP. So do follow that. It will help you guys revising your theory, revising your concepts. Okay, and for feedback, I have been getting requests for the feedback as well. So what we follow here is we do not ask feedback through some link or some form. Instead, what we do is we ask people to share their feedback on the LinkedIn page itself. Okay, so for this live session, there must be a post on the LinkedIn page. Okay, so go in the comment section, share your feedback, whatever you felt, a genuine feedback and honest feedback. You do not have to write all the positive, you can write the negative as well if you find any negative. Okay, does that sound good? Can you guys comment in the chat window? Okay, we have responses pouring in. Sapna says yes. Can we have a few more responses, please? Okay. Okay, Sanat Lakshmi says yes. Sanat Lakshmi has been very active on our Instagram channel as well as in our live sessions as well. So thank you, Sanat Lakshmi, for being with us for every live session and being so interactive on our Instagram handle as well. That help us understanding like how the people are perceiving the content that we are sharing. Okay, thank you, Nitish. Thank you, Arvind. Okay, please contact more. Please conduct more and more sessions. We have comment from Gupta. Yes, Gupta, that's what we are doing right now. So we have sessions on each Sunday. Right now, timings are 8 to 10 p.m. But we can change it if we get enough responses from you guys for other timings. Okay, so make sure that you guys cast in your votes as I requested earlier also. I have shared you the link already for the poll. Okay, so if we see, okay, you guys are comfortable with some other timing, then we'll conduct the live sessions accordingly. Hands-on and theory together will be more interesting, sir. There is a comment from Arvind Patel. Arvind, as I said earlier, like that's what we have been doing. We supplement theory with the practical knowledge. We show the implementation using Python. But in today's session, that has not been covered because topic itself is very vast. So this practical part or implementation part we'll cover in the next live session. So do not worry. That's what we follow, supplementing theory with the practical. Okay. And I'm pasting the link of the post where you need to put your feedback. Okay. So this is the link. Let me know if you guys are able to open up this link. Meanwhile, Ankush, could you please open this link and confirm me if you are able to access this post?
Yeah, which link? This LinkedIn.
Link, yes, I have just pasted post link where we have put up the poster for this live session.
Yeah, I'm checking.
Yes, sir, it's open, sir.
It's open, right?
Yes.
Okay, so please share your feedback on this post. Okay, so if you are, could you guys all confirm, like if you are able to get the same post, the post that we are talking about, live session poster for today's topic? Just quickly tell me in the chat window. We have response from Jagdish saying that better plan the session from 6 to 8 p.m. We'll definitely do it, sir, if we have responses are coming in for 6 to 8 p.m. From all the participants or maximum number of participants.
The reason being, sir,
yes,
beyond the class hours, that will be comfortable for the students, and that should not be on 9 p.m.
Okay, so do we have any classes running in the colleges between 8 to 10?
Might be because the students are about to preparing for their placements. Also, a placement season is ahead.
Okay.
So that students will be engaged till 5 p.m.
Okay.
So it will be better to go with from 6 to 8 or 6 to 8:30.
6 to 8:30. Okay. Feedback taken.
That will be a suggestion from my end, sir. But students are the students are actually they are going to join the session.
Yes. Feedback taken. We are considerate about the people's response. You know. So what we'll do is, instead of taking a biased decision, we have opened up the poll. So it's the students' responsibility to cast their vote about the timing, what timing is comfortable for them. Okay, so please encourage all the students from your college to cast the vote about the timing, so we can come to a common timing that works out best for all. I respect your suggestion, sir.
Yeah, thank you, sir.
Yeah, thank you so much, sir. Okay, so now we have responses saying that yes, sir. Okay, sir, but I'm a bit confused. Like, for what is it? Is it for the post that I was asking for? Whether you guys are able to open up that post or not? Okay, we have Arvind Patel saying that. Thank you so much, sir, for this wonderful session. Okay. Okay, so I'm making assumption that you guys are able to open up that particular post, the post that I'm talking about. post about the poster of this live session, where you guys need to go and share your feedback in the comment section. So it will help us doing two things. Okay, it will help us reaching the more data science practitioners or more data science enthusiasts like you guys. Okay, so we are sharing all this knowledge with at free of cost, basically, where other institutes are charging a hefty amount of money. That's where we want to make sure that we deliver the same knowledge at no money, I mean free of cost, basically. So make sure that you guys give a thumbs up wherever you see our content, whether it's Facebook, Instagram, or LinkedIn, because that's how algorithms work. If you interact with one post, then it will be shown to other people in your friend circle. Okay, so I'll request you guys to be very active on our LinkedIn page, like the post that we share on the page, share your opinions in the comment section. If you think this content is helping you guys, then share it on your timeline on the LinkedIn. As we all know that how the social media algorithms work. So yeah, and we'll be releasing the content on our website as well. So for that, you have to be very interactive on our LinkedIn page, so we know, okay, people are enjoying the content. Okay. Okay. Thank you, Sai. Thank you all. If we do not have any questions, then we wrap up this call. Can you guys say yes in the chat window if we are good to wrap up this call? Yes, Shivam, we'll be sharing all PPT, all the content that's been talked about in this session, free of cost. Content will be live on our website. It will be live on our LinkedIn page also. So make sure that you follow the LinkedIn page to keep check on when the content is out, when the next live session is coming, what the live session will be all about. By the way, just a heads up, we'll be conducting a session about how to submit your own research paper as well. So I hope most of you guys who are really passionate about the data science, they want to submit their own research paper. So I'll request you guys to keep check on all pages, so you do not miss out on that session. Okay. Thank you so much, everyone. Have a happy weekend. Good night. Take care. Happy learning.